What if the most terrifying landscapes imaginable were not the product of nightmares, but rather the universe beyond our own? Imagine a place where the very laws of nature conspire to create environments so hostile, so unforgiving, that even the most advanced human technologies stand no chance of survival. From the blistering sulfuric atmosphere of Venus, where clouds of corrosive acid swirl ominously above, to the volcanic chaos of Io, a moon that constantly reshapes itself through fiery eruptions, the planets and moons that populate our solar system are as varied as they are terrifying. Each presents its own brand of horror, a unique challenge to the limits of human endurance and imagination. Consider Mercury, where the sun's searing heat transforms its surface into an unrelenting furnace, scorching anything that dares to set foot upon it. Or Mars, whose dusty surface hides secrets beneath, a barren world that may harbor ancient dangers waiting to be uncovered. These celestial bodies are more than just distant orbs. They are cruel environments where even the slightest misstep can be fatal. Join us as we journey through some of the most terrifying planets and moons in our universe, each one a testament to the power of nature and the harsh realities of space. Venus, often dubbed Earth's evil twin, is perhaps the most hostile of all. The moment you set foot on its surface, the suffocating atmosphere would crush you. This toxic shroud is not just composed of any gases, but of carbon dioxide in overwhelming concentrations, with clouds of sulfuric acid swirling through the skies in a seemingly endless storm. The air pressure on Venus is over 90 times that of Earth's, creating a force strong enough to flatten even the most durable spacecraft. It's a weight so oppressive that it would crush most human-designed vehicles in an instant. The temperatures on Venus are so high that they rival the inside of an industrial oven set to the highest setting. These infernal conditions melt metals, turn rocks to dust, and render most materials unrecognizable. What might seem like a trivial experiment on Earth would be rendered futile in this hellish landscape where technology buckles under the immense heat. But that's not all. The clouds of sulfuric acid that dominate Venus's atmosphere are so corrosive that any spacecraft sent to explore it would face near certain destruction. Within hours, the chemical fury would tear apart the most advanced materials, leaving only rust and failure behind. And then there's the darkness. Unlike Mercury, which experiences extreme fluctuations in temperature due to its lack of atmosphere, Venus is permanently shrouded in thick, impenetrable clouds. These clouds block out the sun entirely, casting the planet into an eternal twilight. The crushing pressure, the toxic air, and the ceaseless clouds create a perfect storm of hostile conditions, making Venus one of the most extreme frontiers in the universe. It's a place where technology and human endurance are tested to their absolute limits, and where even the most sophisticated missions are at risk of failure. In comparison to other planets, Venus is a true outlier. While Mercury, the closest planet to the Sun, experiences scorching heat on its sunlit side, its lack of atmosphere means it can cool dramatically on the dark side, offering some reprieve. But Venus is different. Its thick atmosphere traps heat in a runaway greenhouse effect, making the surface hotter than Mercury's, even though it is farther from the Sun. The constant, unrelenting heat is not merely uncomfortable, it's deadly. No earthly creature could survive in such an environment, and any human attempt to explore Venus would almost certainly end in catastrophe. Even when compared to other planets in our solar system, Venus stands alone in its extreme conditions. Earth, our home, offers a delicate balance of temperature and atmosphere that supports life. Mars, with its thin, cold atmosphere, might be inhospitable, but it offers a chance for exploration and discovery. In contrast, gas giants like Jupiter and Saturn, though far larger, do not present the same intense heat. The unique and terrifying conditions on Venus, blistering heat, crushing atmospheric pressure, and toxic clouds, make it a world that defies human understanding and presents an insurmountable challenge to exploration. But it's not just the heat and pressure that make Venus so inhospitable. The very nature of its atmosphere is a nightmare in itself. Imagine standing on the floor of the deepest ocean with the crushing weight of the water pressing down on you from all sides. Now, replace the water with thick clouds of sulfuric acid. This is the pressure on Venus. It's more than 90 times greater than what we experience on Earth at sea level, a force so powerful that it could easily crush spacecraft, making any mission to explore the planet an almost impossible task. But the pressure is only the beginning. The atmosphere itself is a chemical hazard. Composed almost entirely of carbon dioxide, it is an inhospitable soup of gases that suffocates and corrodes. Every material sent to Venus must be engineered to withstand these harsh conditions, as the corrosive clouds tear apart everything they come into contact with. For spacecraft, this means that every inch of the vehicle must be designed with precision to resist corrosion. It's a race against time, as any failure of the technology could result in a swift and catastrophic loss of the mission. But perhaps the most dangerous aspect of Venus is the heat. Temperatures soar to levels that no human or machine could endure for long. On the surface, the heat exceeds the temperatures found in most industrial ovens, rendering almost all electronics useless within a matter of hours. Even the most advanced heat shields and materials quickly degrade, making any exploration effort a monumental risk. The combination of blistering heat, crushing pressure, and corrosive gases creates an environment so hostile that survival seems like an impossible dream. Venus stands as a chilling reminder of what might have been. Its size, mass, and composition make it a twin to Earth in many ways. But its environment is the antithesis of everything that sustains life. While Earth flourishes with life, protected by a breathable atmosphere and a mild climate, Venus is a barren, hostile world that mirrors Earth only in the most terrifying ways. It is a place where the promise of exploration gives way to the grim reality of destruction, where technology fails and where human ingenuity faces its greatest challenge. In the end, Venus is not just a planet. It is a cosmic test, an unyielding frontier that pushes the boundaries of what we know about space exploration. It is a world of extremes, a place where every attempt to explore it faces the overwhelming forces of nature. Yet, despite its terrifying conditions, Venus continues to beckon, a challenge to human curiosity and a reminder that the universe is filled with dangers beyond our wildest imagination. Venus, often known as Earth's sister planet, presents a strikingly different reality from our own world, with its unique and extreme environmental conditions. One of the most fascinating aspects of Venus is its remarkably slow rotation on its axis, leading to drastic variations in temperature between day and night. Unlike Earth, which enjoys a relatively balanced cycle, Venus's day-night cycle creates a hostile environment. With a day on Venus lasting longer than its year, the planet's slow spin means that each side is subjected to prolonged exposure to either the blazing heat of the sun or the oppressive cold of the night. This extreme temperature difference sets Venus apart, serving as a stark reminder of how the slightest shift in planetary dynamics can result in an uninhabitable world. Where Earth nurtures and supports life through a harmonious blend of its atmosphere and conditions, Venus embodies the grotesque side of planetary beauty. Its stunning cloud cover hides a nightmarish landscape of crushing pressure, intense heat, and volcanic activity. This contrast between our nurturing home and the inhospitable Venus showcases the fine lines that separate planets capable of harboring life from those that hold only lethal challenges. Through such comparisons, we gain profound insights into what makes a planet habitable, pushing Venus to the forefront of planetary exploration. The study of Venus is not just a matter of understanding our solar system, but is deeply intertwined with the broader quest to discover whether life could exist elsewhere in the vast universe. Turning our gaze to Mercury, the closest planet to the Sun, we encounter another extreme world, one notorious for its perilous temperature fluctuations. Mercury's proximity to the Sun makes it a true outlier in our solar system, exposed to the most intense solar radiation. Under the unforgiving sunlight, surface temperatures can soar to unimaginable levels, reaching highs that could easily melt metal. Yet, this is just one side of Mercury's cruel paradox. The planet has no substantial atmosphere to retain heat, and when the sun sets, the temperatures plummet with a rapidity that leaves no room for survival. The contrast between the blistering heat and the bone-chilling cold is one of the most extreme temperature swings found in the entire solar system, making Mercury a realm where life, as we know it, is entirely out of the question. Imagine a world where, in just a few hours, you can go from heat so intense it could vaporize any exposed material, to cold so severe that even the strongest metals would freeze solid. The relentless shift between these two extremes, day after night, shapes Mercury's surface, contributing to its cracked and fractured terrain. The minerals in Mercury's crust expand and contract in response to these rapid temperature changes, further warping the planet's surface. The lack of atmosphere also exposes the planet to frequent meteoroid impacts, with no buffer zone to soften the blows. These impacts reshape the surface, adding to Mercury's hostile nature and reinforcing the idea that this planet is one of the harshest environments in our solar system. Mercury's landscape, devoid of life and inhospitable to any form of existence, tells the story of violent collisions and geological upheavals. Upon closer inspection, we find an abundance of craters, each one a relic of the planet's tumultuous history. These craters, varying in depth and shape, speak to the diverse range of impacts Mercury has endured over billions of years. The sheer number of these craters, along with their hauntingly varied forms, serves as a testament to Mercury's violent past. Some craters are deep and jagged, while others appear almost smooth, suggesting they formed at different times in the planet's history, under different circumstances. Among these craters lies a particularly notable feature, a vast impact basin that dwarfs any similar formation on Earth or the Moon. This enormous scar on Mercury's surface looks like a giant eye gazing out into the void of space, a reminder of the ferocity of the forces that shaped it. To imagine the catastrophic power behind such an impact is overwhelming. Massive objects hurling through space at unimaginable speeds, crashing into the planet with the force of 1,000 explosions, leaving behind permanent scars. The impact basins, together with the craters scattered across the surface, speak to a planet that has long since been battered by the violence of the cosmos. As we delve deeper into the features of Mercury's craters, we encounter even more eerie phenomena. In some areas, circular formations surrounded by dark, smooth material hint at volcanic activity or the release of superheated gases from beneath the surface. These volcanic remnants and the interplay between impacts and volcanic forces add layers of intrigue to Mercury's history. The planet, though seemingly lifeless today, appears to have once had a far more dynamic past, with events that shaped its landscape in ways we are only beginning to understand. The experience of observing Mercury's desolate, scarred surface is compounded by the extreme environment in which it exists. As temperatures swing from blistering heat during the day to frigid cold at night, the surface seems frozen in time, a testament to the violent history and inhospitable nature of the planet. Viewing Mercury's terrain evokes a profound sense of eeriness, as though we are looking at a world locked in a perpetual state of decay, untouched by time. Yet, beneath this haunting exterior, Mercury stands as a crucial witness to the history of our solar system. A planet whose scars tell the story of countless impacts, volcanic events, and the relentless forces of nature that shaped it. Mercury's role as the closest planet to the Sun exposes it to some of the harshest environmental conditions in the solar system. Its proximity to the Sun results in extreme temperature fluctuations, as it receives an enormous amount of solar radiation. This causes daytime temperatures to skyrocket, reaching levels high enough to melt metals. But without a substantial atmosphere, Mercury cannot retain heat, and when the sun sets, the planet experiences a dramatic plunge in temperatures. This rapid shift between extreme heat and cold, combined with Mercury's fast orbit around the sun, creates a unique and hostile environment. Mercury completes one full orbit in just 88 Earth days, which means that it spends less time in any one position relative to the sun. This swift movement contributes to the planet's dramatic temperature disparities, as the sun's rays strike the surface with ever-changing intensity. Mercury, a planet of extremes, remains an enduring symbol of the challenges of planetary survival. Through its brutal temperature swings, its violent surface, and its unique geological features, Mercury offers a chilling reminder of how precarious life can be and how finely tuned the conditions for habitability must be. It is a world that starkly contrasts with the life-supporting conditions of Earth, inviting us to reflect on the delicate balance required to sustain life and the crushing extremes that can render a world inhospitable. Furthermore, the planet's rapid rotation, coupled with its virtually non-existent atmosphere, results in an unyielding onslaught of solar winds that sweep relentlessly across its surface. These solar winds constantly batter Mercury, gradually wearing down its features and sculpting the planet's surface over time. This dynamic creates a barren, inhospitable landscape, one marked by deep craters, jagged rocky outcrops, and vast plains of hardened lava, all of which stand as a testament to the planet's violent and tumultuous geological history. The interplay of extreme environmental conditions and the harshness of its location reveals a world shaped by ceaseless cosmic forces. Overall, Mercury's proximity to the Sun, combined with its rapid orbit, results in an environment unlike any other in the solar system. It is a world defined by extreme contrasts, constantly fluctuating between intense heat and cold, and perpetually bombarded by unrelenting solar radiation. Surviving a single day on Mercury would be a monumental challenge, one that demands not only resilience, but advanced technology. A day on Mercury lasts about 58 Earth days, owing to its slow spin, while its year, its complete orbit around the Sun, takes only 88 Earth days. This peculiar rotation gives rise to one of Mercury's most extreme features, its day-night cycle. When the Sun rises over the planet's surface, daytime temperatures soar to scorching levels, hot enough to melt certain metals. Yet when the Sun sets, the temperature plummets to frigid depths, dropping well below freezing. This stark contrast between heat and cold is exacerbated by the lack of a significant atmosphere to buffer the temperature swings. In such conditions, shielding would be essential for survival. To stand any chance of withstanding the extreme daytime heat and nighttime chill, one would need a structure designed to endure Mercury's hostile environment. It would have to offer insulation from the brutal sunlight during the day, while also trapping heat during the icy nights. The sunlight itself would be harsh and unfiltered, bombarding surfaces directly due to the absence of a protective atmosphere, thus presenting yet another hazardous challenge. Without air to breathe, any would-be survivors would need a portable life support system, a self-sustaining solution that would provide oxygen, heat, and protection from the relentless solar radiation. Mercury's surface is desolate and alien. Scattered with craters from impacts over billions of years, vast stretches of rocky plains are punctuated by relics of the planet's violent geological past. The planet's lack of water, save for trace amounts in permanently shadowed craters at the poles, further underscores its inhospitable nature. Any surviving organism would find little to sustain it here. Water, essential for life, is almost entirely absent, and the very atmosphere that could provide protection from the Sun is nearly non-existent. Mercury is a world where life, as we know it, could not thrive without advanced technology and specialized resources beyond our current capabilities. In this unforgiving environment, surviving even a single day on Mercury would demand an unprecedented level of human ingenuity and resilience, showcasing just how extreme life can be beyond our home planet. Mars, on the other hand, presents a landscape that evokes a sense of both beauty and desolation. It is a world shaped by geological forces that have left behind dramatic features, vast volcanic plains and colossal volcanoes that tower above the surrounding landscape. The largest of these, Olympus Mons, is so vast that it dwarfs the tallest mountains on Earth, rising to an unimaginable height with a summit that houses a vast caldera, forming an awe-inspiring and forbidding profile. This immense volcano, along with the other towering volcanic structures scattered across the Martian surface, adds to the planet's mystique and grandeur. In addition to the volcanoes, Mars is defined by its massive system of canyons, most notably Valles Marineris. This enormous canyon system stretches thousands of kilometers across the Martian surface, creating deep chasms that slice through the rocky terrain. The steep cliffs and shadowy depths of these canyons contribute to the sensation of an inhospitable environment, one that is both alien and majestic in its scale and appearance. The interplay of light and shadow, combined with the vast emptiness, evokes a profound sense of isolation and grandeur. Mars's surface is also dominated by dusty, reddish soil, a color that gives the planet a desolate, lifeless appearance. The vast, barren plains are punctuated by craters left behind by asteroid impacts, reinforcing the planet's ancient, pockmarked visage. These craters speak to the planet's turbulent history, each one telling a story of cosmic collision and geological upheaval. At the poles, the ice caps, composed of frozen carbon dioxide and water, add an unexpected contrast to the planet's otherwise barren appearance. From afar, these polar ice caps can appear strangely beautiful, framing the planet with their icy purity. However, Mars's unforgiving climate and extreme temperature fluctuations render these regions, like the rest of the planet, largely uninhabitable. Each of these features, the towering volcanoes, the immense canyons, the barren plains, and the polar ice caps, works together to define Mars's intimidating character. They speak of a planet that was once dynamic, perhaps more Earth-like in its distant past, but now stands as a stark reminder of the geological forces that have shaped it. Mars has long captured the imagination of humanity, and its geological features serve as a haunting reminder of what the planet once was and what it has become. One of the most compelling aspects of Mars is its history with water. There was a time, long ago, when scientists believed Mars was a vibrant world, rich in liquid water, oceans, rivers, and lakes that covered its surface. However, the present-day Mars is a dry, dusty landscape, marked by the remnants of ancient riverbeds and mineral deposits that suggest water once flowed freely. Images taken from orbit reveal valley systems and canyon walls shaped by the erosion of liquid water, giving credence to the idea that the planet was once a more hospitable place. But what happened to that water? The disappearance of liquid water on Mars is a central mystery that has captivated scientists for decades. Geological evidence, including the presence of ancient riverbeds and lake basins, suggests that water once played a significant role in shaping the Martian surface. Yet the surface of Mars today is dry, with only trace amounts of water found in the form of ice at the poles and possibly in subterranean reserves. The absence of liquid water raises profound questions about the planet's past climate and the processes that led to its transformation. Did Mars lose its atmosphere, causing the water to evaporate into space? Did the planet's internal dynamics change, leading to a dramatic shift in its surface conditions? The absence of liquid water adds an eerie dimension to the mystery of Mars. The planet's transformation from a potentially Earth-like world to the desolate environment we see today is a stark reminder of the fragility of planetary climates and the delicate balance required to sustain life. The idea that Mars could have supported life at one point in its history, perhaps even a thriving ecosystem, is both captivating and tragic. Scientists continue to study the remnants of the planet's watery past, trying to unravel the mystery of how Mars changed so dramatically and whether life in any form might have once existed there. Massive dust storms on Mars further complicate the planet's already harsh environment. These storms are a defining feature of the Martian atmosphere, capable of sweeping across the entire planet and obscuring the surface in a thick veil of dust. Winds during these storms can reach speeds of up to 100 miles per hour, creating an environment that can feel oppressive and unyielding. These dust storms are not merely a nuisance. They have a profound impact on the Martian climate. When the storms occur, they can temporarily raise the surface temperature by trapping heat in the atmosphere, creating conditions that could exacerbate atmospheric changes and further alter local weather patterns. The dust particles themselves reflect sunlight, darkening regions of the planet and potentially disrupting weather systems, creating a feedback loop that could intensify future storms. These storms are a constant, shaping the atmosphere and climate of Mars in ways that are still not fully understood. In many ways, Mars serves as a reminder of the delicate balance required to sustain life on a planet. Its ancient history, once filled with water and possibly life, contrasts sharply with its present state, dry, dusty, and inhospitable. The vanishing of water on Mars remains one of the most poignant mysteries of our solar system, urging scientists to look beyond Earth and explore what happened to this enigmatic world, as well as what it might reveal about the future of other planets in our galaxy. The Martian landscape, with its towering dust storms, remains one of the most enigmatic and formidable aspects of Mars exploration. These storms, often sweeping across the entire planet, create an atmosphere of extreme volatility. The dust, thick and pervasive, cloaks the Martian terrain in a dense blanket, reducing visibility to such an extent that even from the vantage point of space, the planet's surface features become nearly impossible to discern. This abrasive and unpredictable environment poses significant challenges, not only for the robotic explorers that traverse its surface, like the rovers, but also for any future human missions. Navigating through such a thick atmosphere, where visibility is perpetually compromised and equipment is continually buffeted by fine, abrasive dust particles, would test the limits of human ingenuity. These dust storms are more than just an inconvenience. They transform Mars into a planet constantly in flux. The atmosphere shifts erratically, and the surface is often marked by massive swirls of dust. Understanding these storms is essential for grasping the complexities of Martian weather patterns and its geological history. They paint a picture of a planet that is as dynamic as it is unforgiving, an environment where the laws of nature seem to be in a constant state of flux, making Mars as intriguing as it is treacherous. Exploring Mars has revolutionized our understanding of this mysterious neighbor, revealing tantalizing glimpses into its past. Early missions focused on photographing the surface and gathering basic data, but as technology advanced, these missions unearthed something far more profound, evidence suggesting that Mars may have once harbored conditions conducive to life. One of the most groundbreaking discoveries came through the analysis of both the surface and atmospheric data. This revealed that in its distant past, Mars was a much warmer and wetter place. Rivers and lakes likely dotted its surface, and possibly even an ocean stretched across its expanse. Mineral deposits, which form in the presence of liquid water, further support the theory that Mars once possessed a far more hospitable environment. Rovers like Curiosity and Perseverance have been instrumental in digging deeper into Mars's soil and rocks, uncovering organic molecules, considered to be the fundamental building blocks of life. While these findings do not confirm the existence of life, they strongly suggest that the necessary ingredients for life as we know it may have been present. Additionally, the detection of methane emissions, seen to occur seasonally, adds another intriguing layer. On Earth, methane is often linked to biological processes, hinting that similar, potentially microbial life forms might have once thrived on Mars. Furthermore, the discovery of spectacular sedimentary structures on Mars, shaped by ancient water flows, closely resembles formations found on Earth, especially in areas teeming with microbial life. These findings continue to bolster the theory that Mars could have supported life in its distant past. The identification of regions on Mars that have experienced various environmental conditions throughout history offers additional insight into how habitats may have shifted, making it possible that Mars once offered a dynamic range of ecosystems, each potentially supporting different forms of life. As international collaborations continue and missions build on each other's findings, our understanding of Mars only deepens. Each new discovery strengthens the belief that the red planet has a complex and storied history, one that may offer the key to understanding whether we were ever truly alone in the vast expanse of the cosmos. The quest to uncover the secrets of past life on Mars fuels scientific inquiry and inspires future exploration, urging us to look more closely at the Martian surface and beyond, into the mysteries of the universe. Meanwhile, in the distant reaches of the cosmos, an exoplanet named Kepler 438b stands as a fascinating case study in the search for habitable worlds. Located roughly 600 light-years away, Kepler 438b orbits a star in what's known as the habitable zone, the region around a star where conditions might allow liquid water to exist, a key ingredient for life as we know it. This positioning makes the planet a prime candidate in the search for life beyond Earth. However, despite its favorable location, Kepler 438b presents a host of challenges that complicate its potential to support life. For one, it is slightly larger than Earth, categorizing it as a super-Earth. This means it possesses much greater gravity than our home planet, a factor that could significantly alter atmospheric conditions. The planet's increased gravity raises concerns about whether Kepler 438b could retain a stable atmosphere capable of supporting life. If the planet is located too close to its star, intense radiation could strip away its atmosphere, especially if it lacks a strong magnetic field to shield it. Such atmospheric erosion could prevent the planet from maintaining the conditions necessary for life. The nature of Kepler 438b's host star adds further complications. It orbits a red dwarf star, an M-type star, known for its frequent and powerful stellar flares. These energetic outbursts could shower Kepler 438b with harmful radiation, potentially rendering its environment hostile to life. Despite these challenges, Kepler 438b's location in the habitable zone and its potential for water have made it a compelling subject of study. This juxtaposition of favorable conditions alongside the threat of intense radiation forces scientists to reconsider their models of habitability. While proximity to a star and the presence of water are essential, they do not guarantee a safe environment for life to flourish. Kepler 438b serves as a reminder that habitability is a far more nuanced concept than previously thought. Kepler 438b underscores the complexities of the search for life beyond Earth. It highlights the need for a multifaceted approach, one that accounts not only for a planet's location in the habitable zone, but also for the nature of its environment and the activity of its host star. This realization has profound implications for our search for life in the universe. It challenges the assumption that planets in the habitable zone are necessarily safe havens for life. The Kepler 438b system reminds us that life, if it exists elsewhere in the universe, may take forms that are vastly different from anything we can currently imagine, shaped by conditions that we are only beginning to understand. As we peer farther into the cosmos, the discovery of planets like Kepler 438b and the continuing exploration of Mars urge us to expand our definition of what constitutes a habitable world. It pushes us to rethink the boundaries of life and to consider environments that might once have supported it, even if those environments no longer exist in their original form. The ongoing pursuit of knowledge through both robotic missions and astronomical discoveries continues to challenge our assumptions and drive us to explore the possibility that life may indeed exist elsewhere in the universe. This journey not only deepens our understanding of the cosmos, but also of ourselves and our place within it. Fluctuations in solar activity, particularly those linked to the eruption of solar flares, can dramatically alter the climate and temperature of distant worlds, setting in motion a cascade of effects that reach deep into the atmosphere. When a solar flare erupts, it releases staggering amounts of energy, far more than the Earth's surface typically experiences. This surge in energy can heat the atmosphere of a planet almost instantly, creating the possibility for extreme and erratic weather patterns. These changes in atmospheric conditions can have profound implications for habitability, affecting the ability of any biosphere to thrive. In the case of exoplanets like Kepler 438b, the dynamics of a star's solar activity are far more than just an interesting scientific observation. They can be decisive in determining whether life as we know it could ever exist. The habitability of planets orbiting distant stars may hinge on more than just their proximity to those stars. The nature of the stellar activity, particularly how dynamic or violent it is, plays a pivotal role in shaping the potential for sustaining life. When examining a world like Kepler 438b, it's not enough to look at its distance from the star alone. The planet's very future could depend on how much solar radiation it is exposed to, and whether the star's flares are frequent and intense enough to disrupt the planet's atmosphere. The relationship between a planet's atmosphere and its ability to shield itself from harsh radiation is complex. A thick atmosphere might provide some level of protection, but this is not a guarantee of survival. If the stellar activity persists for extended periods, even the thickest of atmospheres might fail to offer any meaningful defense. The nature of solar flares can be highly unpredictable, and their ability to strip away an atmosphere altogether is one of the great threats to planetary habitability. The dynamic solar phenomena surrounding Kepler 438b don't just affect its climate. They have the potential to fundamentally alter the conditions under which life could exist, if it exists at all. Kepler 438b has captured the attention of scientists and astronomers alike, not only because of its potential to support life, but also due to the inherent dangers that come with its location and environment. Orbiting a star similar to our Sun, this exoplanet resides within the so-called habitable zone, the sweet spot where temperatures might be just right for liquid water to exist on its surface. Liquid water, as we know, is an essential building block for life. However, despite these promising conditions, the planet presents a stark paradox. Kepler 438b is much larger than Earth, likely making it a super-Earth, a planet with a much stronger gravitational pull than our home planet. This increased gravitational force has significant implications for the atmosphere. A thicker atmosphere would trap more heat, potentially creating conditions of extreme temperature. The planet's proximity to a red dwarf star only exacerbates these risks. Red dwarfs are infamous for their unpredictable flares, which emit intense radiation, including harmful ultraviolet rays and X-rays. These radiations can strip away the atmosphere of a planet over time, rendering it inhospitable. Though Kepler 438b's position within the habitable zone suggests the possibility of liquid water, this promising feature is continually undermined by the harsh environmental factors at play. In addition to the radiation hazards, Kepler 438b faces the threat of geological instability. The size of the planet, coupled with its star's gravitational influence, could lead to intense tidal forces, triggering volcanic eruptions and tectonic shifts. These geological upheavals would likely contribute to a volatile surface environment, perhaps making the planet uninhabitable in ways that are not yet fully understood. The combination of high radiation levels, intense stellar flares, and seismic activity suggests that, while Kepler 438b offers tantalizing possibilities for life, it is also a reminder of how challenging it is to find Earth-like conditions beyond our solar system. Turning our attention to one of the most fascinating and volatile worlds within our own solar system, Io, one of Jupiter's moons, we witness an entirely different but equally extreme environment. Io's surface is marked by relentless volcanic activity, unlike anything found on Earth. Imagine a world where volcanoes erupt with astonishing frequency, spewing ash and molten lava into the air. This constant volcanic turmoil is powered by tidal heating, a process driven by the immense gravitational forces exerted by Jupiter. As Io orbits its massive parent planet, it is constantly stretched and compressed, generating vast amounts of heat beneath its surface. This heat fuels the eruptions, creating towering fountains of lava that can reach miles into the sky. The landscape of Io is a chaotic blend of vibrant colors, brilliant yellows, reds, and browns that come from various sulfur compounds and silicate materials ejected during volcanic events. The moon's surface is dotted with vast plains of volcanic deposits and towering mountains formed by lava flows. Each eruption reshapes the terrain, creating an ever-changing and hostile environment. Despite the violence of these geological forces, the surface of Io remains a place of eerie beauty, a living testament to the power of nature and the forces that govern the cosmos. However, Io's surface is not the only remarkable feature. The moon's atmosphere is incredibly tenuous, primarily composed of sulfur dioxide, which provides little protection from the harsh conditions. While the surface of Io can be extremely cold, volcanic activity creates localized pockets of heat. This bizarre contrast creates a unique and unsettling environment. Volcanic plumes vent into space, reshaping the surface as they cool and solidify, offering a glimpse into the moon's tumultuous and violent geological history. Despite the constant turmoil, Io remains a fascinating object of study. Each volcanic eruption provides clues to the inner workings of the moon, shedding light on the powerful forces at play beneath the surface. These volcanic events don't just reshape the landscape, they reshape our understanding of celestial bodies, challenging our perceptions of what is possible in the universe. Io is a world of contradictions, a place where extreme conditions combine to create an environment that is at once hostile, dynamic, and oddly beautiful. As one of the largest moons of Jupiter, Io stands as a testament to the extraordinary gravitational forces that dominate our solar system. The intense tidal forces that arise from Jupiter's massive gravity lead to some of the most extreme geological phenomena seen anywhere in the cosmos. These forces stretch and compress Io, generating the heat necessary to fuel its volcanic eruptions, making it the most volcanically active body in our solar system. The constant volcanic activity reshapes the surface in real time, turning Io into a world in constant turmoil, where geological upheaval is a daily occurrence. Beyond the volcanic eruptions, the intense radiation from Jupiter's magnetic field adds another layer of hostility to Io's environment. This radiation interacts with the moon's surface, ionizing particles and creating a thin, ever-changing atmosphere. This dynamic environment is unwelcoming to life forms, but it is also a fascinating study in the resilience and variety of celestial phenomena. The auroras and radiation-related effects that arise from these interactions add a strange, otherworldly beauty to Io's environment, highlighting the complex and powerful forces that shape not only the moons of Jupiter, but all celestial bodies within the gravitational reach of massive planets. In the end, Io serves as a reminder of the unpredictable and often inhospitable nature of the universe. It offers a glimpse into the volatile processes that can shape planets and moons, creating environments that are both mesmerizing and terrifying in equal measure. Just as Kepler 438b represents the fine balance between hope and danger in the search for life beyond Earth, Io stands as a vivid example of the power and unpredictability of nature in the cosmos. The harsh realities of these distant worlds challenge our understanding, but they also fuel our curiosity and drive to explore the unknown. Caught in an eternal struggle, Io, one of Jupiter's many moons, is entangled in a powerful gravitational tug-of-war with its neighboring moons, Europa and Ganymede. The forces at play create fluctuations in Io's orbit that are not merely captivating, but hold the potential to disrupt the moon's already volatile state. These gravitational interactions can cause shifts in the tidal heating of the moon, sparking even more intense geological upheavals. It is this constant ebb and flow, the unrelenting forces pushing and pulling on Io, that create a dynamic environment where the very structure of the moon could one day be pushed to its limits. The combined gravitational forces from Jupiter and its moons render Io a place of chaos, a celestial battlefield where volcanic eruptions and atmospheric instability seem to reign supreme. For explorers and scientists, this serves as both a stunning reminder of the violent beauty of the cosmos and a warning about the potential dangers of such immense celestial forces. Io's landscape is a living canvas, constantly reshaped by the most extreme volcanic activity in the entire solar system. The moon is enshrouded in a thin, sulfurous atmosphere that, though tenuous, plays a crucial role in the formation of its otherworldly characteristics. The atmosphere is dominated by sulfur dioxide, giving Io its distinctive yellowish and orange hue, a stark contrast to the cold, distant reaches of the solar system. It's a color palette that feels almost alien, as though the moon exists outside the realms of anything we could recognize as familiar. The atmosphere itself is highly dynamic, directly influenced by the fierce volcanic activity that defines Io. Massive plumes of sulfur and sulfur dioxide erupt from the moon's surface, sometimes reaching heights that surpass those of many of Earth's tallest volcanoes. As these eruptions take place, they release sulfur into the thin atmosphere, continuously reshaping the moon's surface with the shifting of gases and their interaction with the rocky terrain below. This volatile interaction between gases and surface materials creates a constantly evolving topography, one filled with volcanic pits, rivers of lava, and vast sulfur lakes that seem to come alive in a flash of heat and color. The surface of Io is in a state of perpetual flux, the scars of new eruptions quickly erasing any trace of previous geological activity. But the thin atmosphere does not offer the kind of stability one might expect from a celestial body. Instead, it contributes to a feeling of isolation, intensifying the harsh and unforgiving nature of this distant moon. The lack of protective shielding means that Io's surface is bombarded by intense radiation from Jupiter's immense magnetic field, adding to the already inhospitable conditions. The radiation, coupled with extreme fluctuations in temperature, further exacerbates the hostile environment. These extreme conditions not only leave their mark on the surface, scarring the terrain with radiation damage and temperature extremes, but they also result in the creation of colors and patterns that seem wholly unnatural. Each volcanic eruption produces unique hues, and as the gases disperse into the atmosphere, they give rise to an ever-changing spectacle that seems more like a surreal dream than a physical reality. It is a landscape that evokes both awe and unease, a reminder of the immense forces shaping the cosmos and the fragility of existence in the shadow of such powers. Yet, for all its danger, Io is a captivating celestial body. The The volatile geology and harsh atmosphere create a moon that is as mesmerizing as it is terrifying, a vivid reminder of the constant turmoil shaping our universe. Its surface is a dynamic tableau of fire and color, of chaos and transformation. It is a place that commands both respect and fascination, a world where the forces of nature are as raw and unfiltered as anywhere in the solar system. The heart of Io's geological activity lies in the immense tidal forces generated by Jupiter's powerful gravity. Imagine being caught in a cosmic tug-of-war as Io orbits its massive parent planet. Jupiter's gravitational pull repeatedly stretches and compresses the moon, a process known as tidal heating. This friction generates immense internal heat within Io, which fuels its continuous volcanic eruptions and reshapes its surface. In a sense, Io is a planet caught in an eternal cycle of rebirth, its surface constantly resurfaced by eruptions that spew gas and molten rock into the thin atmosphere. Some eruptions are so powerful they can project plumes of material high into the sky, often reaching altitudes far greater than Mount Everest. This relentless volcanic activity results in a surface that never stays the same for long, a characteristic that sets Io apart from many other celestial bodies, which are either geologically inactive or long dead. Beyond the violent eruptions, Io's surface is a riot of color. Fiery reds, yellows, and browns mark the locations of volcanic vents and fissures. These colors reveal the different volcanic materials and compounds that are expelled from the moon's interior during eruptions. Remarkably, there are almost no impact craters on Io's surface. This absence of craters is a testament to the moon's geological youth. Any signs of past collisions are quickly erased by the constant volcanic resurfacing. The harsh environment of Io further intensifies its volatile nature. Temperatures drop to bone-chilling lows during the night, while radiation from Jupiter continuously bombards the surface, leaving it scarred and inhospitable. Only the hardiest forms of life, if any life exists there, might endure such conditions. Despite its menacing and volatile nature, Io remains a tantalizing target for scientists. Its extreme geological activity provides a rare opportunity to study the processes that drive planetary evolution, offering valuable insight into the mechanisms of planetary formation and the potential for life in extreme environments. The study of Io not only deepens our understanding of the complex interactions at play in our solar system, but it also stirs our imagination. As we look at this strange and tumultuous moon, we are reminded of the wild, untamed beauty that lies in the farthest reaches of space. Elsewhere in the universe, scientists have turned their gaze toward the enigmatic pulsar PSR B11257 plus 12c, a neutron star that presents a completely different set of challenges. Pulsars are rapidly rotating neutron stars that emit beams of radiation from their magnetic poles. As these beams sweep across space, they can be detected as regular pulses of energy, akin to the ticking of a cosmic clock. The discovery of planets orbiting pulsars is a fascinating and mysterious prospect, but it also raises many questions about the formation and survival of celestial bodies in such extreme environments. The most pressing concern revolves around the intense radiation and high-energy environment created by the pulsar's emissions. This radiation, composed of powerful X-rays and gamma rays, could be catastrophic for any nearby planets. The high-energy bursts would strip away the atmospheres of any orbiting planets, rendering them hostile and barren. This poses a significant challenge to the possibility of life in such environments, as the extreme radiation could destroy any potential biosphere before it had the chance to develop. Yet, despite the inhospitable conditions, the discovery of planets around pulsars is not without intrigue. It challenges our understanding of planetary formation and survival, and offers new insights into the adaptability of life in some of the most extreme conditions the universe has to offer. As scientists continue to study these cosmic phenomena, they are forced to reconsider everything we thought we knew about the limits of life and the potential for habitability in the most hostile corners of the universe. The universe, as we are learning more every day, is far more dynamic and unpredictable than we ever imagined. The gravitational forces exerted by a pulsar, such as PSRB 1257 plus 12c, differ dramatically from the forces we experience in our solar system. These extraordinary forces can give rise to extreme tidal effects that could potentially distort a planet's shape or alter its rotation and orbit in unexpected ways. The immense density of the pulsar's gravitational field creates a complex and hostile environment, one that challenges our understanding of how matter behaves under such conditions. As a result, predicting the geological and atmospheric dynamics of planets that orbit pulsars remains a formidable task for researchers. For planets like PSRB 1257 plus 12c, their relationship with their pulsar is more than just gravitational. It's a close and often captive interaction. The planet orbits in a tight elliptical path around the pulsar, subjecting it to periodic flares and radiation bursts that periodically flood the planet's surface with high-energy particles. The proximity to such a stellar object makes any form of potential habitability exceptionally difficult, if not entirely impossible. Understanding how life, if it could exist, might survive in such hostile, fluctuating environments offers rich scientific insights. However, the challenges are considerable. The behavior of matter, from atmospheric composition to geological activity, in a pulsar's intense gravitational field is still not fully understood. The pulsar's powerful gravitational forces act like an anchor, pulling the planet ever closer, shaping its trajectory and influencing its physical characteristics. The planet's orbit becomes tightly bound to the pulsar, making it predictable, but also constraining the dynamics of the planet's environment. These tidal forces are so strong that they not only influence the orbit, but also help maintain or disrupt the planet's geological and atmospheric conditions. This powerful gravitational pull does more than just affect the orbit of PSRB 1257 plus 12c. It also shapes its physical landscape in profound ways. The planet's atmosphere, if it has one at all, may be unstable and constantly bombarded by high-energy radiation. The pulsar's rotating beams of electromagnetic radiation, which include bursts of gamma rays, X-rays, and high-energy particles, can strip away atmospheric layers from any planet unlucky enough to be too close. These energetic waves can lead to temperatures fluctuating wildly, creating an environment where the surface conditions are harsh and unpredictable. But this is not the full extent of the pulsar's influence. Its immense gravitational field distorts space-time itself. This warping effect can create environments that are drastically different from anything seen in our solar system, including extreme tidal forces that cause massive fluctuations in the planet's structure. The constant shifting of the planet's shape under these forces can lead to continuous seismic activity, creating unpredictable geological phenomena. These disturbances may even give rise to volcanic activity or cause tectonic plates to shift, which, in turn, could change the planet's surface composition over time. Moreover, these gravitational and radiation forces don't just influence the planet's atmosphere and geology, they also affect the very nature of the planet's material composition. The extreme conditions under which PSRB 1057 plus 12c formed, conditions influenced heavily by the nearby pulsar, could mean that its surface is composed of elements or minerals that are entirely foreign to us. These materials may have evolved to withstand the harsh conditions brought about by the pulsar's gravitational and radiation forces. The planet's landscape, if one could even describe it as such, would likely be filled with oddities, forms of matter, structures, and compounds that defy our conventional understanding of planetary geology. The environment around PSRB 1257 plus 12c is not just unique, it's one of the most extreme imaginable. The planet's surface is constantly exposed to radiation, making it almost certainly unsuitable for life as we know it. If you could somehow stand on this world, the relentless bombardment of radiation and the ever-shifting gravitational forces would serve as a constant reminder of the immense power of the cosmos. The experience would be equal parts terrifying and awe-inspiring. The surface temperature would likely fluctuate wildly, and any atmosphere that might exist would be constantly in flux, struggling to maintain its stability against the pulsar's influence. At the heart of this cosmic drama is the pulsar itself, a highly magnetized rotating neutron star that emits intense beams of electromagnetic radiation. This pulsar, like others, rotates rapidly, sending beams of gamma rays, X-rays, and high-energy particles across vast stretches of space. PSRB 1257 plus 12c, being in close orbit to this pulsar, is bombarded constantly by these intense radiation bursts. Imagine a planet caught in the unrelenting glow of a cosmic spotlight, an environment where the surface conditions are sculpted not by the warmth of a distant sun, but by the violent flares and radiation pulses from a rapidly rotating neutron star. The pulsar's radiation not only bombards the surface of the planet, but also affects its environment in more subtle ways. This energy can heat up the planet's surface, creating extreme temperature swings and potentially destabilizing any form of atmosphere. The planet could experience sudden bursts of radiation, resulting in a cataclysmic heating of the atmosphere, further compounding the challenges for habitability. The surface conditions may include intense temperatures, extreme pressure, and the constant threat of radiation poisoning, all of which make life in any conventional sense incredibly unlikely. The combination of these forces, the gravitational pull of the pulsar, the intense radiation, and the resulting geological instability, makes PSRB 1257 plus 12c one of the most hostile environments in the universe. And yet it stands as a testament to the resilience of planetary systems, a reminder of how far our assumptions about the viability of life and the nature of planetary existence can be pushed. The study of such planets offers us a deeper understanding of the universe, as well as the extreme limits of astrobiology. By studying these enigmatic worlds, scientists can expand our knowledge of the conditions that might support life, and, conversely, the conditions that make survival impossible. The more we learn about pulsar systems, the more we realize how varied and diverse the environments of other planets might be, and how different they can be from anything we experience on Earth. Despite the seemingly insurmountable challenges posed by these extreme environments, PSRB 1257 plus 12c stands as a key to unlocking the mysteries of the cosmos. It is a world shaped by the immense forces of a pulsar, an environment that challenges not only our scientific understanding, but also our imaginations. What we discover in studying these worlds could change the way we think about habitability, life, and the very nature of the universe itself. The bombardment of energetic particles from space can gradually strip away a planet's atmosphere, particularly if that atmosphere is thin to begin with. This is the case for PSRB 1257 plus 12c, where the delicate layers of atmosphere are vulnerable to erosion under the intense influence of radiation. As a result, any potential atmosphere that might have once existed is at risk of being completely dissipated, leaving the planet's surface exposed to the unforgiving vacuum of space. Without an atmosphere to regulate temperature or offer protection, the surface of this distant world would be subjected to extreme and fluctuating temperature conditions. The searing heat of pulsar radiation would scorch the surface during periods of exposure, while the cold of space would freeze it in total darkness. The radiation from the pulsar, however, does not only threaten the stability of the atmosphere, it also gives rise to secondary particles and triggers a series of complex chemical reactions on the planet's surface. These reactions, fueled by energetic impacts, could result in the formation of exotic materials, possibly unlike anything found on Earth. The radiation-induced chemical processes and the potential loss of the atmosphere create a hostile and brutal environment on PSRB 1257 plus 12c. This combination of destructive forces, constantly reshaping the surface and altering the composition of the planet, makes it an intensely unique and inhospitable place in the cosmos. Yet, for all its harshness, it remains a fascinating object of study, an extreme world shaped by forces beyond our immediate comprehension. Similarly, Titan, Saturn's largest moon, presents a captivating mystery for scientists and astronomers alike, drawing attention with its strange and eerie landscapes. Its most remarkable feature lies in the vast lakes and rivers of liquid methane and ethane that dominate its surface. Imagine a world where temperatures are so low that water cannot exist in its familiar liquid state, instead remaining as solid ice. Titan's surface is home to a complex system of hydrocarbon lakes, features that, at first glance, resemble Earth's own lakes and rivers, but with one critical difference: their composition and behavior are entirely foreign. The lakes and rivers on Titan are not mere stagnant bodies of liquid. They are dynamic systems that continuously reshape the surface through erosion and the deposition of sediments. The cycle of weather and erosion on Titan is driven not by water, as it is on Earth, but by methane. Methane rains down from the thick, hazy atmosphere to fill the basins, driving a cycle that mirrors the Earth's hydrological processes in many ways, but with a haunting inversion. This cycle, where methane replaces water, raises intriguing possibilities about the nature of life. Could life evolve in such an alien environment, where familiar processes unfold in unfamiliar ways? The stillness of Titan's lakes adds to the eerie atmosphere of this moon. On Earth, when we gaze upon a body of water, we often see the reflections of life and movement, ripples created by the wind or creatures breaking the surface. On Titan, however, the vast expanses of liquid methane are frigid and lifeless. Their stillness contributes to an overwhelmingly alien atmosphere, one that feels strangely devoid of biological activity. Titan's thick, hazy atmosphere only amplifies this sense of isolation, creating a smog-like veil that mutes the sunlight and distorts visibility. The surface is bathed in a diffused light that gives the entire world an otherworldly, almost surreal glow. Yet, beneath the stillness of these lakes, Titan may harbor the conditions necessary for complex organic chemistry to unfold. Though it may be difficult for us to comprehend, the conditions beneath Titan's thick, frozen methane layer could potentially provide a unique environment for life to thrive. The possibility that beneath this inhospitable surface, life might exist, or at least have the potential to exist, is a concept both intriguing and unsettling. Titan presents a paradox, a world with familiar processes occurring in ways that are utterly alien, raising questions about life's adaptability in the most extreme conditions. The atmosphere of Titan plays a crucial role in shaping the moon's distinctive environment. This thick, nitrogen-rich atmosphere with a significant presence of methane creates surface pressures greater than those found on Earth. These pressures, combined with the peculiar nature of Titan's atmosphere, have far-reaching effects, from influencing potential weather systems to determining the stability of liquids on the ground. One of the most striking aspects of Titan's atmosphere is how it interacts with sunlight. The intense ultraviolet radiation from the sun triggers chemical reactions among the atmospheric molecules, producing a variety of complex hydrocarbons. These organic compounds contribute to the moon's characteristic hazy orange color, creating a stunning, mysterious visual effect. The atmosphere also plays an essential role in Titan's weather patterns, particularly in relation to methane. Just as Earth experiences rainfall, Titan, too, experiences precipitation. Only, instead of water, it rains liquid methane and ethane. Imagine, if you will, the clouds on Titan forming from a dense, fog-like haze of hydrocarbons. These clouds eventually release their contents, creating rivers and lakes that fill the lowlands of Titan's surface. Over time, these hydrocarbon rains have sculpted the landscape, carving valleys and creating various features across the moon's surface. The presence of these hydrocarbon rains further emphasizes Titan's alien nature, where organic chemistry might unfold in ways that differ radically from anything seen on Earth. Titan's unique environment and the possibility of life, or at least chemical processes, unfolding within its liquid hydrocarbons make it a compelling candidate for the study of life beyond Earth. The interaction of a thick atmosphere combined with methane rain and an ever-changing surface presents an intriguing and dynamic system that could support entirely different ecosystems under radically different conditions than those we are familiar with. However, the image of Titan as a possible haven for life or scientific exploration belies the more dangerous realities of the moon's surface. The temperatures on Titan are far below freezing, creating an environment that is incredibly hostile to human life and most Earth-based technology. Any equipment sent to Titan would need to be specially designed to withstand these extreme cold conditions. Without such adaptations, any technology would quickly malfunction or become obsolete, making future exploration a daunting challenge. Thus, Titan, Saturn's largest moon, is not just a place of haunting beauty and profound mystery. It is also a world that presents both immense scientific opportunities and significant technological challenges. It offers an extraordinary paradox: a world with features that mimic the conditions of Earth, yet surrounded by conditions so alien and inhospitable that they make it almost impossible for us to imagine what it would take to survive there. But that very mystery makes Titan an object of endless fascination, one that promises to reveal more about the nature of life and the limits of possibility in our universe. Furthermore, the surface of Titan is enveloped in a dense, hazy atmosphere that severely restricts visibility, creating a significant challenge for both navigation and exploration. While the allure of Titan's hydrocarbon lakes is undeniable, they could harbor chemical reactions that are as yet unknown, potentially hazardous to any mission. The possibility of unpredictable interactions with any materials introduced into this environment presents substantial risks, making Titan's surface a treacherous terrain for both scientific instruments and human explorers alike. The potential for groundbreaking discoveries on Titan is certainly compelling, yet the risks involved are equally formidable. Balancing these two extremes, promise and peril, will be crucial for the success of any mission aimed at uncovering the secrets this enigmatic moon holds. Titan, Saturn's largest moon, is a world of stark contrasts, where immense size collides with an inhospitable climate. To put it into perspective, Titan is larger than Mercury, showcasing its impressive scale within our solar system. This vast size is crucial, as it not only allows for a thick, dense atmosphere, but also sets the stage for the extreme conditions that dominate its surface. The key to understanding Titan lies in its extraordinary composition. It is primarily made up of water ice and rocky material, giving it a solid and stable foundation, yet its atmosphere is the most remarkable feature. Thick enough to obscure any direct view of the surface, it consists mainly of nitrogen, much like Earth's atmosphere, but it contains little oxygen. Instead, Titan's atmosphere is rich in hydrocarbons, complex organic compounds that give it a distinctly alien character. This combination of gases and compounds creates an environment that is drastically different from our own. Titan's surface is marked by intensely cold temperatures that plummet far below anything Earth's biosphere can tolerate. At these frigid levels, methane turns into a liquid, forming vast lakes and rivers that carve the landscape. These methane bodies, along with clouds of methane rain falling from the atmosphere, make Titan's weather system utterly unique. Here, methane takes on the role of water, crafting a completely different hydrological cycle from anything we know. Despite its frozen exterior, Titan is far from lifeless. It is a world where methane plays the role of water, creating rivers, lakes, and clouds in a way we would never expect. But this harsh, cold environment poses severe obstacles for exploration. The thick clouds, the biting cold, and the pervasive presence of liquid methane and ethane combine to make Titan an incredibly fascinating yet dangerous world. Any mission to this moon would need to be specially equipped to withstand these extreme conditions, while also considering the potential for prebiotic chemistry, the tantalizing possibility that life could exist or have once existed in some form. The sheer scale and composition of Titan, coupled with the strange compounds that fill its atmosphere, create a narrative both breathtaking and bleak. It stands as a reminder of the extraordinary variety that exists within our solar system, where immense worlds with unimaginable conditions coexist with the notion that life might, one day, be found on a moon so alien that it challenges everything we know about habitability. In another corner of the universe, HD 1897333b offers its own brand of terror. Located about 60 light-years from Earth, this exoplanet captivates the imagination with its extreme weather phenomena. This distant world orbits its star at such a close distance that it experiences scorching temperatures and unrelenting atmospheric conditions. The winds on HD 1897333b are unlike anything on Earth. They rage at speeds so ferocious they could put even our most powerful hurricanes to shame. Imagine standing next to a howling, unstoppable storm, only to find that this one is capable of reshaping the planet's atmosphere itself. What truly makes HD 1897333b an unsettling place, however, is the phenomenon of glass rain. The planet's high surface temperatures, combined with its intense atmospheric pressure, create conditions conducive to the formation of silicate particles. These particles, lighter than air, condense into glass-like materials, which are then flung across the planet by the relentless winds. As they fall back to the surface, they descend at incredible speeds, turning a simple downpour into a dangerous, deadly storm. The glass rain, coupled with hurricane-force winds, results in a hostile environment where survival is impossible for any known form of life. The dynamic interplay of these extreme conditions paints a vivid picture of a world that is not merely inhospitable, but downright terrifying. The tempestuous atmosphere of HD 189733b showcases the kinds of extremes that the universe can produce, expanding our understanding of planetary atmospheres and their potential consequences. For any explorer or mission to venture to this world, the challenges would be staggering. The atmosphere, charged with glass shards and whipped into furious storms, would render any attempt at exploration a perilous endeavor. The temperature alone would create a massive barrier, with surface heat so intense that it could melt metals, making human exploration and equipment placement almost impossible. To explore HD 189973b, new innovations would be required. Heat-resistant materials that could withstand the searing temperatures, while also being lightweight enough to make transport viable. Every piece of technology sent to this planet would need to be specially designed to survive conditions that surpass anything Earth's most resilient machinery could endure. It is a stark reminder of the immense challenges posed by exoplanets, where the weather is not just extreme, but downright lethal. And yet, within this chaotic realm lies the potential to learn more about planetary atmospheres, the extreme forces of nature in May, and the incredible diversity of worlds in the cosmos. The challenges posed by the atmospheric composition of HD 18973b are numerous and staggering. This distant exoplanet is primarily dominated by carbon dioxide, with high-altitude clouds of silicate particles swirling through the hostile environment. The atmosphere here is not just toxic, it's a lethal mix that makes breathing air impossible. Any potential explorers to this planet would have to rely entirely on life support systems, bringing their own oxygen and ensuring the removal of dangerous carbon dioxide from their habitats. These life support systems would need to be incredibly reliable, as the planet's extreme conditions would demand constant attention to ensure the safety and stability of the explorers. Survival. But even with these systems in place, the challenges don't end. The surface of HD 189733b is no less treacherous. With atmospheric pressure far greater than what we experience on Earth and winds fierce enough to surpass the speed of sound, navigating this world would be a feat of extreme endurance and skill. The terrain itself can shift dramatically, and the ever-changing weather patterns could present sudden and dangerous atmospheric phenomena that would be impossible to predict. Advanced navigation technology would be essential here, systems designed not only to withstand the planet's extreme conditions, but also to provide explorers with the ability to adapt to a world where nothing is certain and everything is a potential hazard. Exploring HD 18973b would demand groundbreaking technological innovation at every step. From crafting materials capable of surviving the crushing pressures and intense heat, to creating life support systems that can keep explorers alive in a constantly hostile environment, each milestone would be a testament to human ingenuity and perseverance. This endeavor would underscore the resilience and determination that drives humanity to explore the farthest reaches of the universe, no matter how inhospitable or forbidding the destination might be. The planet's extreme nature leaves no room for error, and yet the human spirit's desire to push boundaries remains unwavering. HD 189733b is a textbook example of an extreme environment. Orbiting perilously close to its parent star, this exoplanet is subjected to blistering temperatures that soar far beyond anything Earth's atmosphere can endure. The intense heat warps the atmosphere into a chaotic, hostile realm, a searing furnace that would make even the hardiest Earth organisms struggle to survive. As if the sweltering heat weren't enough, HD 1899733b is also plagued by violent winds, relentless gales that sweep across the surface at mind-boggling speeds, faster than the speed of sound itself. These forces combine to create a setting that is as inhospitable as it is fascinating. But there is yet another danger that makes the planet even more unwelcoming: the atmosphere itself. Thick clouds composed of silicate particles resembling glass are carried by the brutal winds. These clouds aren't just a visual spectacle, they are a perilous hazard. The sharp, glass-like particles rain down on the surface, turning the landscape into a deadly gauntlet. Imagine a world where the sky isn't just filled with heat and fury, but also with shards of glass that tear at anything unfortunate enough to be exposed. It's a harsh, unrelenting environment where every moment spent on the surface could be a battle for survival. In this unforgiving atmosphere, HD 189733b stands as an extreme outlier in our understanding of habitability. Its environment, defined by heat, wind, and silicate particles, presents a stark contrast to the idea of a habitable world. This alien world defies our expectations of what is necessary for life. Yet, despite the unimaginable conditions, it raises an interesting point about the resilience of life itself. After all, life on Earth has been discovered thriving in environments once thought impossible for survival: extreme depths of the ocean, scorching hot springs, and even acidic lakes. These discoveries suggest that life might not be bound by the conditions we are familiar with. On HD 189733b, the possibility remains that, despite the extreme conditions, some form of life could exist, though we are far from understanding the exact nature of such life. While the atmosphere of HD 18973b is undeniably lethal to humans, life as we know it might not be the only possibility. Future research could uncover biochemistry entirely alien to us, organisms utilizing chemical processes radically different from the carbon-based systems on Earth. These organisms might even thrive in conditions that we would consider impossible for life to exist. However, as of today, any talk of life on this planet remains purely speculative. Understanding Earth's own extreme environments and the life forms that thrive within them is key to guiding our future explorations beyond our solar system. It will shape how we approach planets like HD 18973b and whether we might one day find life in places that are truly alien to our understanding. Meanwhile, the exoplanet Gliese 581g presents a different, though still extreme, scenario that ignites both excitement and caution among scientists. Orbiting a red dwarf star, this planet is located within what's known as the habitable zone, the region around a star where conditions might allow liquid water to exist, and thus potentially support life. The mere prospect of water on Gliese 581g stirs excitement, as it increases the likelihood of finding life similar to what we know on Earth. But while this is thrilling, it is not without its own set of challenges. The atmosphere of Gliese 581g, for instance, could be vastly different from Earth's. The surface conditions could be extreme, high pressures and temperatures unlike anything we experience. If the planet's atmosphere contains thick layers of greenhouse gases, it could generate surface temperatures that push the boundaries of what we understand as survivable. And the weather patterns? We might struggle to comprehend them fully, let alone predict their effects on potential habitats. Thus, while the possibility of life on Gliese 581g sparks curiosity, it also serves as a reminder of how little we know about the far reaches of our universe, and how much we must learn to truly understand the environments that exist beyond our world. Exploring exoplanets like HD 18973b and Gliese 581g pushes the limits of our knowledge and technology. It forces us to ask not only how we can survive in extreme conditions, but also how we might one day thrive in environments vastly different from our own. Each discovery, each new planet explored, brings us one step closer to understanding the true scope of life's potential in the universe and the boundless possibilities that await in the final frontier. The gravitational influence of a nearby star system can introduce a series of unpredictable tidal forces that may have a profound effect on the planet's structure as well as its climate. These forces, unpredictable in nature, heighten the stakes of exploration. A careful survey of the planet's atmosphere could unveil a range of gases, potentially signaling biological processes at work. On the other hand, the presence of certain gases might indicate an environment that is hostile to life, possibly even toxic. This uncertainty, woven into the fabric of scientific inquiry, makes this exoplanet, Gliese 581d, a subject of particular fascination and caution in the quest to discover life beyond our own world. Gliese 581d occupies a critical and intriguing position in its star's habitable zone, a region often described as the Goldilocks zone. where conditions may be just right for liquid water to exist on a planet's surface. This concept is crucial because, as we understand life, water is an indispensable ingredient. Picture this zone as a delicate balance, not too close to the star, where temperatures soar to unbearable extremes, and not too far, where freezing cold dominates. As Glia 581d orbits its host star, it receives just the right amount of energy to sustain liquid water, creating an environment in which life could, in theory, flourish. Yet, there is more to this picture than mere proximity to the habitable zone. The planet's surface characteristics, its atmosphere, temperature stability, and any geological activity add layers of complexity to its potential to host life. A thick atmosphere could help regulate temperature and shield the planet from harmful cosmic radiation. Diverse terrain might foster a range of ecological niches, each contributing to the evolution of different forms of life. The surface conditions, coupled with the planet's size, suggest that Glia 581d is a super-Earth, meaning it is significantly larger than Earth, which results in a stronger gravitational pull. This extra mass could alter the planet's ability to retain its atmosphere, which could, in turn, influence the planet's capacity to maintain the conditions necessary for life. The atmospheric and geological features of Glia 581d add further layers of uncertainty and intrigue. These factors could create a diverse range of environments, from temperate regions suitable for life to harsh, inhospitable zones. The potential for biological processes is not guaranteed. The environment might support life, or it could be a barren world, too volatile for even the most resilient organisms. Researchers remain tirelessly focused on studying Glia 581d and other similar exoplanets, seeking to understand the complex web of factors that might allow life to thrive in such distant and alien worlds. Indeed, Glia 581d presents a paradox. Its location in the habitable zone raises thrilling possibilities about the existence of liquid water and, by extension, life. Yet, this very promise is tempered by the unknowns of its environment, making it a symbol of both excitement and caution in the search for extraterrestrial life. This dynamic of exploration filled with equal parts awe and apprehension forms the essence of what makes Glia 581d such a compelling object of study for astronomers and astrobiologists alike. As we continue to unravel the mysteries of the universe, Glia 581d holds a unique place in our quest to understand not only how life could arise elsewhere, but also the vast, untapped potential that the cosmos might offer. Glia 581d, classified as an exoplanet orbiting within the habitable zone of its red dwarf star, offers scientists a tantalizing glimpse into the types of environments that could harbor life. The atmosphere on this distant world could give rise to extreme weather patterns, driven by both the size of the planet and its unusual orbital characteristics. The larger-than-Earth size of Glia 581d suggests that its atmosphere is likely thick and dense, which, combined with its orbital mechanics, could produce violent weather systems. Since the planet is tidally locked, meaning that one hemisphere permanently faces its star while the other remains in perpetual darkness, the temperature disparity between the two sides would be stark. On the sunlit side, the temperatures could be scorching, while the dark side would experience unrelenting cold. This extreme contrast in temperatures could lead to intense thermal gradients that spawn fierce winds, as the atmosphere attempts to equalize the temperature between the two sides. These winds could potentially reach astonishing speeds, driven by the dramatic difference between day and night temperatures. If Glia 581d has a composition that includes significant amounts of water, its weather could become even more tumultuous. The constant heating on the star-facing side could lead to boiling oceans, while on the dark side, the cooling could cause condensation to form, resulting in sudden downpours or massive storms. The presence of thick clouds could lead to cycles of rain and drought, potentially creating environments where life could struggle to adapt to the shifting weather patterns. These unpredictable cycles would further complicate the potential for biological processes, as any emergent life forms would have to contend with violent storms and extreme temperature fluctuations. In addition to intense temperature gradients and cloud formations, extreme weather systems could also be driven by the composition of the planet's atmosphere. If there is enough water vapor in the air, Gliese 581d could experience violent lightning storms, fueled by the intense heat and electrical activity accumulating in the atmosphere. The interplay between surface temperatures, atmospheric pressure, and water vapor could create a perfect storm for dramatic weather events, making the planet both a captivating and ominous world to study. Red dwarf stars, like the one that powers the Gliese 581 system, are key players in shaping the environment of orbiting planets. These stars are much smaller and cooler than our Sun, which means that their habitable zones are located much closer to the star. This proximity can have profound implications for the conditions on nearby planets, such as Gliese 581d. While the star's lower luminosity means it emits less light and heat than our Sun, it still provides enough energy to sustain liquid water on the planet's surface, as long as the planet's atmosphere and surface conditions are conducive to life. However, this closeness to the star has its drawbacks. The fact that Gliese 581d is tidally locked means that one hemisphere is always facing the star, while the other remains in perpetual darkness. This unique arrangement could lead to extreme temperature differences between the day and night sides, creating a volatile environment that is both fascinating and unpredictable. The star's weak luminosity, combined with the tidally locked orbit, creates a world where atmospheric circulation could play a crucial role in regulating temperatures, allowing heat and moisture to move from the sunlit side to the dark side, potentially creating habitable conditions across the planet's surface. As scientists continue to explore the possibilities of life beyond Earth, Gliese 581d stands as both a beacon of hope and a reminder of the complexities that lie within the search for extraterrestrial life. Its unique position in the habitable zone, coupled with the extreme weather and unpredictable conditions that could arise from its tidal locking, make it a fascinating world to explore. While its environment may seem hostile at first glance, the potential for discovery is too great to ignore. And as technology advances, we will no doubt learn more about this enigmatic planet and the possibilities it holds for life beyond our own solar system. Red dwarfs, often regarded as the most common type of star in the universe, possess unique characteristics that shape their environments in ways both fascinating and challenging. These stars are notorious for their longevity, with lifespans extending well beyond the scale of human history, often reaching tens of billions of years. This remarkable stability provides a potential sanctuary for planets orbiting within their habitable zones, like Gliese 581d, allowing ample time for the development of life. But while these stars can offer an environment in which life might flourish, they also present significant challenges. One of the most striking features of red dwarfs is their frequent and intense stellar flares. These bursts of radiation can have devastating effects on nearby planets. The energy released during such flares can strip away a planet's atmosphere, leaving it barren and uninhabitable. Additionally, these flares can alter the chemistry of a planet's surface, complicating the development of life as we know it. So while the red dwarf's long lifespan might initially seem to favor the evolution of life, the unpredictable nature of its stellar activity introduces a layer of uncertainty, creating a precarious balance. For a planet like Gliese 581d, situated within the habitable zone of a red dwarf, this interplay between stability and volatility presents a complex picture. The proximity of the planet to its star means it is likely tidally locked. One side of the planet perpetually faces the star, while the other remains in darkness. This tidal locking results in extreme temperature differences between the day and night sides, which could drastically affect the planet's climate and the potential for life to thrive. The long-term stability of Gliese 581d's orbit is another factor that must be considered. If the planet's orbit remains stable for billions of years, it could provide a sustained environment for life to evolve and persist. However, the hazards posed by the red dwarf's flares and the tidal forces acting on the planet may make the environment unpredictable and hostile. In contrast, WASP-12b represents an extreme example of a planet caught in the grip of a very different kind of stellar environment. This exoplanet orbits so close to its parent star that it is subjected to conditions unlike anything we experience on Earth. The temperature on WASP-12b is staggeringly high, likely exceeding the melting point of many materials found on our planet. The intense heat causes the atmosphere to be thick with vaporized metals and other elements. Titanium, iron, and other heavy metals, which would ordinarily exist in solid or liquid form on Earth, exist as gases in the infernal heat of WASP-12b's atmosphere. These gases contribute to a highly toxic environment, one where survival, at least as we understand it, is virtually impossible. Moreover, the atmosphere of WASP-12b is not only hot, but also under immense pressure, adding another layer of hostility. The planet's extreme proximity to its star subjects it to constant tidal forces, which distort the planet's shape into an oblong rather than a perfect sphere. These forces also create supersonic winds that travel faster than the speed of sound, resulting in atmospheric turbulence that gives rise to violent storms and unrelenting weather patterns. This constant atmospheric upheaval makes the planet a nightmare for any life form that might otherwise struggle to survive. The intense radiation emitted by the star further exacerbates the conditions on WASP-12b. The planet is bombarded with high levels of radiation that not only heat its atmosphere, but also strip away lighter gases over time. This process gradually diminishes the planet's atmosphere, leaving it vulnerable to the vacuum of space. The combination of extreme temperatures, toxic gases, intense radiation, and tidal forces creates an environment where the concept of life as we know it is not just improbable, it is utterly impossible. The planet's unique position so close to its star also creates one of the most extreme climates known to humanity. The gravitational pull exerted by the star compresses the planet's atmosphere, causing it to become incredibly dense. And this heightened atmospheric pressure would be enough to crush any objects from Earth, making the surface of WASP-12b hostile in a way that is almost impossible to imagine. The dense, toxic atmosphere is a hotbed for chemical reactions that result in strange weather patterns and possibly even bizarre phenomena, further complicating any notion of thriving in such an environment. WASP-12b, with its extreme temperatures, crushing pressures, and violent weather, stands as a stark contrast to the more potentially habitable environments that might be found around red dwarfs like Gliese 581d. While Gliese 581d might offer a more stable setting for life to take root, albeit with significant challenges, WASP-12b epitomizes the harsh extremes that can exist in the universe, where any form of life, even in its most resilient form, would face insurmountable odds. This comparison underscores the complexity of exoplanetary environments and the wide variety of conditions under which life might or might not emerge. From the stable yet volatile surroundings of a red dwarf star to the extreme and inhospitable environment of a planet like WASP-12b, the cosmos presents an array of possibilities. Some offer hope for the existence of life, while others make survival an impossible dream. Each of these worlds, with their unique attributes, challenges our understanding of what makes a planet truly habitable and pushes the boundaries of what we know about the forces that shape planetary systems. Furthermore, this planet experiences a phenomenon known as tidal locking, which means that one side perpetually faces its star, while the other remains cast in eternal darkness. This results in a stark division, a dichotomy of extremes that defines the very essence of the planet. One hemisphere bakes under relentless solar radiation, where temperatures soar to extreme levels, while the other side endures an unyielding freeze, with temperatures plummeting into bitterly low ranges. This contrast only deepens the planet's terrifying nature. It is a world where unimaginable heat and bone-chilling cold coexist, and where the forces of nature themselves seem to conspire to make life, or even exploration, impossible. All of these factors, intense heat, high density, and harsh atmospheric conditions, paint a picture of a planet that challenges the limits of human understanding. A planet where the very laws of physics seem to be pushed to their breaking points, marking it as a truly awe-inspiring example of the diversity that exists in the universe. In particular, WASP-12b stands as one of the most extreme exoplanets discovered, captivating scientists and space enthusiasts alike, not just for its massive size or its dangerously close proximity to its parent star, but for the way it interacts with light. Imagine a world with an atmosphere that is an unsettling blend of extremes, creating a surreal spectacle as sunlight plays off its surface. WASP-12b is notorious for being one of the darkest planets known to science, absorbing nearly all the light that strikes it. It resembles the texture of charcoal, as if its surface is a void, drawing in light rather than reflecting it. The light that does manage to bounce off offers tantalizing clues about the planet's atmosphere. Unlike Earth, where we are accustomed to blue skies due to scattering, WASP-12b's thick, oppressive atmosphere absorbs far more sunlight than it reflects. This intriguing characteristic not only makes the planet a visual oddity, but also hints at the complex chemical makeup of its skies. The atmosphere is likely filled with clouds composed of sodium and other metals in gas form, elements that exist due to the planet's intense heat. This provides an otherworldly glow, yet it also raises critical questions about the physical and chemical properties of such a dense and inhospitable environment. The immense gravitational pull of WASP-12b stretches the planet into an oval shape, a result of tidal forces that in turn fuel its intense heat. This, combined with its close orbit around its parent star, leads to fascinating yet unsettling observations. As the planet rotates, its brightness fluctuates rapidly, shifting in a rhythm that's unlike anything we see on Earth. The interplay of light and shadow on this world is erratic and mysterious, a spectacle that challenges our fundamental understanding of atmospheric science. It's a dynamic and dark world, and every observation is a puzzle, a piece of a larger mystery about how such planets form, evolve, and what they can teach us about the variety of worlds that exist in the cosmos. WASP-12b is a reminder that our solar system, with its planets and moons, is only one of countless others that have been shaped by forces beyond our comprehension. It serves as a window into the diversity of planetary environments, marking its place as one of the most remarkable and enigmatic objects in our search for exoplanets. Meanwhile, another exoplanet that has garnered significant attention for its strange and haunting appearance is TRES-2b. Often cited as one of the darkest exoplanets ever discovered, it stands out not just because of its size or location, but because of its remarkable ability to absorb nearly all the light that strikes it. About 97% of the sunlight that hits this planet is absorbed, with only a minuscule fraction reflected back into space. The result is a celestial body that appears to be a nearly invisible blot against the backdrop of the stars. What's behind this eerie darkness? TRES-2b's atmosphere is rich in compounds like sodium and potassium, substances that absorb light rather than reflect it. When light interacts with these elements, it is not reflected, but rather converted into heat, which makes the planet appear as if it is vanishing into the cosmos. The heat that accumulates as a result of this absorption leads to temperatures that are likely far higher than we would expect on a planet with such a low reflectivity. Instead of radiating visible light, much of the energy is emitted as infrared radiation, making it almost impossible to see with the naked eye in the visible spectrum. Against the myriad of stars that dot the universe, TRES-2b presents itself as an eerie, shadowy presence, a stark reminder of how planets can evolve in ways that defy our expectations. As TRES-2b orbits incredibly close to its host star, its high temperatures are thought to play a crucial role in its ability to absorb so much light. The closer proximity to the star likely enhances the planet's capacity to trap energy, preventing any visible light from escaping. The end result is a planet that remains shrouded in an almost perpetual state of darkness, adding another layer of mystery to the already complex nature of exoplanets. The fact that such a planet exists, one that can absorb nearly all the light that strikes it, is a striking challenge to our understanding of planetary atmospheres. The dense clouds, rich in metallic compounds, could explain why the planet is so dark, and this phenomenon prompts researchers to wonder how such extreme conditions can arise and what they reveal about the processes that govern planetary formation and evolution. Is it a clue to the development of other worlds in far-flung regions of the universe? Could there be other TRES-2b-like planets out there, hidden in the shadows of distant stars, waiting to be discovered? In the vast expanse of space, planets like WASP-12b and TRES-2b are not just scientific curiosities. They are profound examples of how diverse and unimaginable the universe truly is. These planets are a stark reminder that even in the cold, dark void of space, there are worlds that defy everything we think we know about physics, chemistry, and life itself. The study of these distant worlds challenges our assumptions and encourages us to imagine the unimaginable as we continue to explore the cosmic wilderness beyond our own planet. The light absorption on TRES-2b offers more than just a glimpse into its mysterious nature. It hints at possible interactions with energy that profoundly affect how the planet radiates heat, influencing its weather patterns in ways we can only begin to understand. The dark surface of this exoplanet not only absorbs nearly all incoming light, but also enhances its thermal efficiency, making it a planet that is both dangerously hot and uninviting. This is a stark contrast to the shimmering, bright worlds we often envision when thinking of distant planets, providing an eerie reminder that not all celestial bodies are welcoming. Some, like TRES-2b, are engulfed in shadow, adding a layer of depth to our ever-expanding understanding of planetary diversity across the cosmos. Known as one of the darkest exoplanets discovered to date, TRES-2b absorbs an astonishing amount of light. Imagine a celestial body coated in a reflective substance so minimal that it barely gleams. This extreme darkness is not just a mere aesthetic trait, it has profound implications for the planet's climate and behavior. Because it reflects less than 1% of the light that hits it, much of the starlight is absorbed, leading to an intriguing lack of heat reflection. As a result, the planet's surface, perpetually shrouded in shadows, experiences extremely low temperatures. With such a minimal reflection of light, the heat that does accumulate does so unevenly, creating significant temperature gradients. These gradients could contribute to atmospheric phenomena such as strong winds or storms that are driven by the stark differences in temperature between various regions. Exploring TRES-2b presents enormous challenges. The lack of brightness makes it difficult for space telescopes to detect the planet, since these instruments typically rely on the light reflected from a planet's surface to capture images and gather data. Moreover, the planet's atmosphere, potentially laden with exotic chemicals, could prove inhospitable to the instruments we use to explore more familiar environments within our solar system. Despite these challenges, the study of TRES-2b remains an exciting avenue of research. Its extreme darkness might provide valuable insights into atmospheric science, particularly concerning how atmospheres evolve in such unusual and extreme environments. Understanding these atmospheric characteristics could pave the way for discoveries about other exoplanets that share similar conditions, ultimately enhancing our knowledge of the diverse range of worlds scattered throughout the universe. TRES-2b's composition and atmospheric dynamics are of particular interest to scientists. This exoplanet is located outside our solar system, orbiting very close to its star, which means it experiences scorching conditions that can surpass the heat of a furnace. These intense temperatures contribute to bizarre atmospheric phenomena, possibly leading to the formation of strange chemical compounds that are not found on Earth. In addition, researchers have observed signs that suggest the presence of luminous, potentially exotic materials within TRES-2b's clouds. These substances could include vaporized minerals or chemicals that are unknown to us, playing a key role in the planet's unusual and obscure atmosphere. The interplay of light absorption, extreme temperatures, and potentially dynamic weather systems creates a fascinating area for exploration. By studying these phenomena, scientists hope to unlock the secrets behind the processes that shape alien worlds, which could broaden our understanding of planet formation and the diverse environments that can exist beyond our own world. The mysteries of TRES-2b continue to fuel excitement and curiosity among astronomers and planetary scientists alike. This distant exoplanet challenges our assumptions about what makes a world habitable, igniting a new wave of interest in the fundamental processes shaping planetary systems throughout the universe. The lessons learned from TRES-2b will likely extend far beyond our study of this particular world, potentially informing our exploration of other exoplanets with similarly extreme conditions. In this way, TRES-2b acts as both a symbol and a window into the untold diversity of the cosmos, where each planet, no matter how dark or seemingly inhospitable, adds richness to our understanding of the universe's boundless complexity. Meanwhile, the discovery of Proxima Centauri b, an exoplanet orbiting the closest star to our solar system, has sparked significant interest in the possibility of life beyond Earth. Proxima Centauri b resides within what is often referred to as the habitable zone, the region around a star where conditions might be right for liquid water to exist, a crucial ingredient for life as we know it. However, this seemingly ideal location does not guarantee that the planet is capable of sustaining life. Proxima Centauri b presents a paradox. While it occupies the habitable zone, it is constantly bombarded by radiation from its host star, Proxima Centauri. This powerful radiation, along with frequent stellar flares, poses a serious threat to the planet's atmosphere, potentially stripping it away over time and creating a harsh and uninhabitable environment. Even though Proxima Centauri b is situated at a distance that could allow for liquid water, the intense radiation from its star might severely compromise the atmospheric conditions necessary for life to thrive. For years, scientists assumed that a planet's location within the habitable zone was a sufficient condition for it to support life. Proxima Centauri b challenges this assumption, demonstrating that the presence of liquid water alone is not enough. Other factors, such as the composition and stability of a planet's atmosphere, as well as its magnetic field, are crucial for determining whether life can exist. The study of Proxima Centauri b forces us to reconsider what we consider habitable, suggesting that even planets in the Goldilocks zone may not always be hospitable to life. This realization has sparked a reevaluation of our understanding of habitability and what conditions are truly necessary for sustaining life beyond Earth. The characteristics of Proxima Centauri, the red dwarf star that Proxima Centauri b orbits, further complicate the potential for life on the planet. Red dwarfs are much cooler and less luminous than our Sun, which places Proxima Centauri b in a location where liquid water could theoretically exist. However, this proximity to its star has significant consequences. It is likely that Proxima Centauri b is tidally locked, meaning one side of the planet is always facing the star, while the other side remains in perpetual darkness. This tidally locked nature creates extreme temperature differences between the two hemispheres of the planet, with the day side potentially experiencing scorching heat and radiation, while the night side could plunge into frigid temperatures. These extreme and potentially unstable conditions make it difficult to imagine how life, as we understand it, could survive on Proxima Centauri b. In conclusion, the discovery of both TRES-2b and Proxima Centauri b serves as a reminder of the complexity and unpredictability of exoplanets. While one is an enigmatic world shrouded in darkness and extreme heat, the other exists in a seemingly ideal location, but faces a relentless barrage of radiation that undermines its potential for habitability. These two exoplanets, in their unique ways, challenge our expectations and push the boundaries of what we thought we knew about the conditions necessary for life. Their exploration continues to captivate scientists, offering endless opportunities for discovery and a deeper understanding of the vast and varied worlds that populate the universe. The conditions on Proxima Centauri b present a unique and challenging landscape, one that could offer glimpses of what life might look like in environments far beyond our home planet, yet it also raises significant questions about the feasibility of habitability. Proxima Centauri, the star around which this exoplanet orbits, is an active stellar body, frequently emitting solar flares that produce powerful bursts of radiation. These flares are far more intense than anything Earth experiences, and they could have catastrophic effects on any atmosphere or life forms that might exist on a nearby planet. The radiation released during these flares is capable of stripping away a planet's atmosphere entirely, leaving it exposed to the harsh vacuum of space. Without a protective atmosphere, any potential for sustaining life would be severely compromised, as the essential elements necessary for life, such as water, would vanish. If Proxima Centauri b were to possess an atmosphere, it would need to be substantial enough not only to provide protection against this constant bombardment of radiation, but also to help stabilize temperatures across the planet. However, the challenge doesn't end there. The high activity of the star would constantly erode this atmosphere, making it difficult to maintain the conditions required for life. Even though Proxima Centauri b resides within the star's habitable zone, an area where liquid water could theoretically exist on a planet's surface, the combination of its star's violent activity, the potential for tidal locking, and the ever-present risk of high radiation presents significant barriers to the development of life. Tidal locking, a phenomenon in which a planet's rotation causes one side to always face its star while the other side remains in perpetual darkness, is another factor that makes Proxima Centauri b a particularly challenging environment for life. In this case, the planet's day and night cycle would be highly irregular, with one side perpetually exposed to sunlight and the other shrouded in eternal darkness. This uneven distribution of energy could lead to extreme conditions, with one side experiencing unrelenting heat and the other plunging into freezing cold. The stark contrast between these environments could prevent the planet from reaching the balanced conditions required for life to thrive, resulting in two radically different climates. Additionally, the atmosphere would play a pivotal role in moderating the temperatures on Proxima Centauri b. If the planet has a thin atmosphere, the heat might not distribute evenly across its surface, which could lead to violent storms or extreme winds as air is forced to move from the hot side to the cold side. On the other hand, if the planet has a thick atmosphere, this could exacerbate the greenhouse effect, causing the planet's surface temperature to rise to unbearable levels, much like the extreme conditions on Venus. In either case, Proxima Centauri b's atmosphere would face a fine balancing act between protecting the planet from harmful radiation and preventing runaway heat, with both extremes potentially hindering the possibility of life. Moreover, the frequent solar flares from Proxima Centauri add another layer of complexity. These flares are not only capable of irradiating the planet's surface, but could also strip away any atmosphere that the planet might have, further increasing the likelihood that the environment would remain inhospitable. The constant bombardment of radiation could leave any planet, particularly one in tidal lock, unable to recover from these periodic bursts, compounding the difficulty for life to take hold. These factors, intense solar radiation, tidal locking, atmospheric erosion, and the planet's position within a star's habitable zone, combine to create an environment that is complex, volatile, and potentially hostile to life. While the prospect of finding life on Proxima Centauri b is intriguing, the conditions presented by these multiple variables suggest that if life does exist, it is likely to be vastly different from what we know on Earth, assuming it can survive at all. To understand the broader implications of this, it is useful to explore how solar flares in general impact life on Earth. Solar flares, which occur when the sun's magnetic fields become tangled and release massive amounts of energy, have the potential to significantly disrupt modern life. These bursts of radiation can affect Earth in a variety of ways, from disrupting radio signals to interfering with satellite communications. In more extreme cases, solar flares can even produce coronal mass ejections, CMEs, which are clouds of solar particles that travel through space and have the potential to damage power grids and other infrastructure. The speed at which solar radiation reaches Earth, traveling at the speed of light, means that even though we can't physically feel the radiation, it can have substantial effects on our daily lives. The impacts of solar flares are most often observed as brief disruptions in communications or minor navigational errors for aircraft and ships, but larger flares can cause far-reaching damage. This is why scientists pay close attention to the sun's behavior, using a variety of instruments and satellites to monitor solar activity in real time. By tracking the patterns of sunspots and identifying fluctuations in solar radiation, scientists can predict flare activity and issue warnings to mitigate the effects on Earth's technological systems. Given our reliance on technology, understanding and responding to solar flares has become an important area of research to protect our infrastructure and way of life. Beyond our solar system, the study of exoplanets such as Proxima Centauri b provides an opportunity to explore these same phenomena in an entirely new context. The unique challenges posed by a planet in a system with an active star can give scientists valuable insights into the conditions necessary for life, as well as the factors that might prevent it from taking hold. While the chances of Proxima Centauri b supporting Earth-like life may be slim, the lessons learned from studying such worlds will continue to shape our understanding of the universe and the diverse environments that may exist within it. In contrast, another exoplanet, GJ-124b, located in the constellation of Ophiuchus, presents a different set of challenges. Classified as a mini-Neptune, GJ-124b is shrouded in a thick, steamy atmosphere that is rich in water vapor and other gases. The surface pressure on this planet would be vastly higher than anything experienced on Earth, potentially making it impossible for any Earth-like life to survive. The dense atmosphere would likely lead to an intense greenhouse effect, with temperatures rising to extreme levels that would make the surface of the planet incredibly inhospitable. This thick atmosphere could also result in the formation of acid clouds, further complicating the prospect of life. The idea of life on GJ-124b is radically different from what we know on Earth. Any organisms that might exist here would likely be adapted to extreme conditions, potentially drawing energy from the planet's unique atmospheric chemistry, or existing in environments so acidic that familiar forms of life could not survive. The potential for bizarre alien life forms capable of thriving in such an environment opens up an entirely new realm of possibilities, challenging our understanding of what life is and how it might arise in places far beyond Earth. In exploring these distant worlds, we are forced to confront the limits of our imagination and the possibilities of life in forms that we cannot yet fully comprehend. Whether it's the harsh conditions on Proxima Centauri b or the extreme greenhouse effect on GJ-124b, these exoplanets present both captivating and terrifying glimpses of what might lie beyond our familiar understanding of habitability, urging us to think in radically new ways about life in the universe. Moreover, GJ-124b, a distant exoplanet, might experience intense high-speed winds driven by the overwhelming heat and pressure disparities within its atmosphere. These winds could unleash violent storms that race across the planet's surface, similar to those seen on gas giants like Jupiter and Saturn. While thick clouds may obscure the view of the planet from our eyes, what lies beneath could be a chaotic world where lightning ignites the darkened skies in sudden powerful flashes. The atmosphere's volatile nature may result in a constant, fierce turmoil, illuminating the planet's surface with bursts of fury. Additionally, GJ-124b's interaction with its powerful magnetic fields could generate electrifying phenomena akin to auroras on Earth, but on a scale far grander and more dramatic. Imagine stunning atmospheric displays casting eerie glows across an alien landscape, each shimmer and streak of light a reminder of the planet's extraordinary forces. The depths of this thick atmosphere may hold even more tantalizing secrets, vast, oceanic bodies of superheated water. In these mysterious oceans, liquid water and water vapor could coexist, forming an environment where extreme chemical reactions take place at every turn. These dynamic and potentially hazardous environments could challenge our very definition of what constitutes life. GJ-124b could indeed be a realm of awe and terror, an alien world perpetually shrouded in steam and pressure, where life, if it exists, would likely defy our understanding. Every element of this world pushes the boundaries of what we consider possible, offering a stunning, albeit harrowing, glimpse into a future where life thrives in environments far beyond Earth's familiar realms. Situated approximately 404 light-years away from Earth, GJ-124b has captivated the scientific community due to its potential to host a vast, deep ocean, a characteristic that has earned it the title of a water world. This possibility is linked to the planet's unique composition and the distinctive conditions that prevail there. GJ-124b is classified as a super-Earth, meaning that it is larger than our planet but still maintains a largely rocky composition. However, its thick atmosphere likely contains significant amounts of hydrogen and helium, creating conditions that trap heat, making the planet's surface much warmer than what we experience on Earth. The temperature on GJ-124b is relatively mild, particularly when compared to the more extreme exoplanets scientists have studied. This raises the possibility that liquid water could exist in substantial quantities on the planet's surface. Should GJ124b harbor a deep ocean beneath its atmosphere, several kilometers deep, it could form a continuous body of water that envelops the entire planet. This concept presents thrilling opportunities for exploration and discovery, including the tantalizing question of whether life could exist in such an environment. However, the idea of a water world on GJ1214b comes with its share of challenges and complexities. One of the primary obstacles to life as we know it lies in the extreme pressures that would prevail beneath the massive layers of water. These pressures could create environments that are inhospitable, possibly rendering them uninhabitable for any form of life familiar to us. The immense depths of the ocean would likely mean complete darkness, a lack of essential nutrients, and an overall hostile environment. Further complicating the potential for life on GJ14b is the possible absence of land masses. On Earth, land is a crucial aspect of environmental processes that allow for the development of life, such as the cycling of nutrients and the formation of ecosystems. In the case of a water world without land, these processes may be significantly diminished or even absent. The planet's thick atmosphere, composed of dense clouds of vapor, could also hinder our ability to observe surface features or fully understand the true nature of the planet's geological composition. Understanding GJ1214b requires grappling with complex scientific challenges, particularly in the fields of fluid dynamics, chemical reactions, and the vast unknowns surrounding potential ecosystems. While the concept of a water world is undeniably captivating, the realities of studying such an environment are fraught with difficulties. The scientific community faces an uphill battle as it attempts to piece together the intricacies of a distant world, shrouded in mystery and ambiguity. GJ124b, a far-off exoplanet orbiting a star in another part of the galaxy, is often described as a place of extremes. These extremes are largely driven by the planet's immense atmospheric pressure, which plays a central role in shaping its environment. To understand the intensity of this pressure, imagine the crushing force felt at the deepest parts of Earth's oceans, where every inch downward becomes increasingly heavy due to the weight of water above. Now, imagine that feeling amplified to an extreme degree. On GJ1214b, this sensation is magnified many times over. The planet's thick atmosphere results in pressures far higher than anything experienced on Earth. The consequences of such immense pressure are far-reaching, leading to drastic alterations in the composition and states of matter. For instance, the pressure on GJ124b might cause water to transition into a dense, nearly solid fluid, rather than maintaining the familiar gas or liquid states we encounter here on Earth. This could trigger the formation of exotic substances or chemical reactions that would be impossible to replicate under normal conditions, making GJ124b a truly hostile and otherworldly environment. In conclusion, GJ124b remains an enigmatic and awe-inspiring world. Its unique features, thick clouds, high pressures, potential water oceans, and powerful magnetic fields, create an environment that is as alien as it is fascinating. The planet's extreme conditions suggest that it is far from a place where life as we know it could survive. Yet the question remains, could life in some form still thrive in such an unforgiving environment? The pursuit of answers to this question pushes the boundaries of our understanding and fuels the ongoing fascination with distant worlds. The intense atmospheric pressure on GJ124b could profoundly influence how temperatures behave, leading to a highly unusual thermal environment. The combination of sweltering heat and crushing pressure can create a situation where heat struggles to escape efficiently, resulting in uniformly high temperatures across the entire planet. This scenario makes the surface conditions even more daunting, creating an atmosphere where the usual patterns of temperature regulation we take for granted on Earth do not apply. Instead of experiencing the more predictable shifts in temperature from day to night, GJ124b may maintain a constant, oppressive heat. Such extremes could foster dynamic weather patterns, possibly leading to violent storms or unrelenting heat that blankets the planet's surface in an atmosphere constantly in motion. These conditions would make GJ124b feel not only alien, but also terrifying, an inhospitable world where the elements are both unpredictable and unyielding. The very forces that shape the planet, heat, pressure, and dynamic weather, combine in such a way that any form of life, at least as we understand it, might seem impossible. What makes GJ124DB even more intriguing is its mysterious yet possibly volatile atmosphere. Discovered orbiting a red dwarf star, the planet resides in a region where conditions are far from the familiar, life-sustaining environments of Earth. Scientists speculate that its atmosphere may be thick, potentially rich in water vapor, though the exact composition remains elusive. The unknown nature of its atmosphere raises concerns about the planet's habitability. In fact, the pressure and temperatures on GJ124b could be so extreme that they prevent any possibility of supporting life as we know it. Worse still, the atmosphere might be laden with harmful substances, or it could be so dense that it prevents meaningful exploration or even observations from reaching its surface. The mysterious interaction between the planet's atmosphere and its geological features only adds to the complexity of understanding this alien world. If the pressure in GJ124b's atmosphere is indeed greater than that found in the deepest trenches of Earth's oceans, it challenges our very notions of habitability. Furthermore, the planet's proximity to its host star, along with the intense radiation it receives, presents additional problems. Over time, this radiation could cause the erosion of the planet's atmosphere, gradually stripping away the essential elements needed for life. These unpredictable factors invoke fear and fascination, highlighting just how much we still have to learn about environments so drastically different from our own. The more scientists delve into the characteristics of GJ124b, the more they uncover its potential to defy expectations. Each discovery not only fascinates those curious about the universe, but also unsettles them as they confront the vast gaps in our understanding of celestial bodies that exist far beyond the boundaries of our solar system. Similarly, Korat 7b is another exoplanet that captures both the imagination and caution of astronomers. Located incredibly close to its star, Korat 7b is exposed to an intense heat that renders its surface nearly uninhabitable. Imagine a world so scorched by relentless sunlight that metals melt and vast seas of molten rock spread across the landscape. The intense heat makes it nearly impossible for the planet to cool, creating a surface dominated by molten rivers and bubbling volcanic plains. One side of Korat 7b is perpetually bathed in scorching light, while the opposite side is locked in perpetual darkness. This stark contrast in temperature creates extreme and dynamic weather systems that defy anything seen on Earth. The day side might be so hot that entire rocks vaporize and billow into the atmosphere, while the night side could plummet to temperatures that would freeze everything solid. This extreme thermal difference results in constant upheaval, where the surface of the planet is in a state of constant flux, perpetually reshaped by the forces of heat and pressure. If Korat 7b has an atmosphere, it is likely thick with toxic gases and heavy clouds, substances that would be familiar in Earth's volcanic environments, but would seem foreign and hostile in this alien landscape. Such an atmosphere would make it difficult to imagine any form of life surviving on the planet's surface, much less thriving. In fact, the extreme heat and constant volcanic activity contribute to the formation of towering mountains made of hardened lava, while rivers of molten material snake across the surface in an endless, fiery dance. In addition to the intense temperatures, Korat 7b is marked by an overwhelming presence of tectonic activity, generating colossal geological forces that lead to violent eruptions. The constant reshaping of the crust and the eruption of gases and molten rock paint a grim picture of a planet in a state of perpetual chaos. In such an environment, it would be hard to imagine the peaceful conditions necessary for sustaining life as we know it. Yet, despite these inhospitable conditions, Korat 7b remains an extraordinary example of the ways in which proximity to a star can drastically alter the nature of a planet. The extreme temperatures, volcanic activity, and the complete lack of liquid water make it a vivid reminder of the diversity of exoplanets beyond our solar system. Each one comes with its own set of challenges, its own harsh environment that pushes the boundaries of what we consider habitable. Korat 7b's surface is not only a place where the rules of habitability as we understand them break down, but also a stark reminder of how fragile the conditions needed for life can be. Without the basics, stable temperatures, liquid water, or a protective atmosphere, this exoplanet serves as a powerful symbol of the hostile, volatile forces at work on distant worlds. Furthermore, the planet's intense volcanic activity is one of the most striking features of its landscape. Volcanic eruptions on Corot 7b are not only constant but incredibly dangerous, spewing molten rock and sulfurous gases into the atmosphere. This gives the planet a fearsome reputation, intensifying the sense of danger and unpredictability that surrounds it. These eruptions, while contributing to the planet's catastrophic surface conditions, also play a key role in its geological evolution, continually reshaping the terrain and altering the chemistry of the atmosphere. In summary, both GJ-12-4b and Corot 7b present worlds that challenge our understanding of what constitutes a habitable planet. They push the limits of temperature, pressure, and environmental conditions to extremes that make life as we know it seem impossible. Yet, these planets continue to captivate scientists, sparking both awe and caution as we peer into the unknown and confront the vast diversity of worlds that exist beyond our solar system. These planets are not simply celestial bodies. They are windows into the extraordinary, sometimes terrifying possibilities of the universe. The intense and unforgiving environment of Corot 7b paints a striking picture of the extremes that can exist beyond our solar system. This rocky exoplanet, located around 600 light-years from Earth, orbits its star with a rapidity that no planet in our solar system could ever hope to match, completing one full revolution in just over 20 hours. This incredibly swift orbit has a profound impact on the planet's conditions, rendering it a place where life as we understand it is virtually impossible. The combination of extreme temperatures and volcanic activity on Corot 7b creates one of the most hostile environments discovered so far in the universe. The planet's proximity to its star means it is subjected to intense solar radiation. The side facing the star is continuously bathed in relentless heat, while the opposite side is locked in permanent darkness. This creates an unyielding temperature gradient between the two hemispheres, which fuels dynamic and violent atmospheric conditions. On the star-facing side, the heat is so extreme that even rocks and metals are melted into a liquid state, forming a molten, shifting landscape that is as deadly as it is alien. Meanwhile, on the dark side, temperatures can plummet to unimaginable lows, causing gases in the atmosphere to condense into clouds or even frost, depending on their chemical composition. This stark contrast between the two sides of Corot 7b, coupled with the tidal forces exerted by the star, results in a synchronous rotation, one where the same hemisphere of the planet always faces the star. This unique configuration amplifies the temperature disparity and generates violent weather patterns, including constant, powerful winds that attempt to balance the dramatic extremes. Such a planet illustrates how the mechanics of orbit, how a planet's position and rotation affect its exposure to its star, can profoundly influence its climate and composition. Corot 7b is not just a curiosity for astronomers. It is an invaluable example of the kind of environments that could exist on planets orbiting distant stars. Its volatile volcanic activity and extreme temperature variations showcase the variety and unpredictability of planetary conditions, offering new insights into the possible climates of exoplanets, especially those situated perilously close to their stars. In contrast to Corot 7b's hostile landscape, Kepler-22b presents a tantalizing yet equally mysterious case of a potentially habitable exoplanet. Located in the habitable zone of its star, Kepler-22b is in the region where liquid water could, in theory, exist, an essential ingredient for life as we know it. Yet several characteristics of the planet complicate the prospects of finding life or even Earth-like conditions there. First, Kepler-22b is significantly larger than Earth, approximately 2.5 times its size. This size suggests that the planet might have a thick atmosphere and high surface pressures, which could lead to extreme weather patterns, including violent storms that would make the environment hazardous. The planet's larger size also implies a stronger gravitational pull, which could alter the behavior of its atmosphere and even the potential for life. The stronger gravity might contribute to a thicker atmosphere, trapping gases such as carbon dioxide and methane, which could amplify the greenhouse effect. This would cause temperatures on the surface to rise to dangerous levels, creating a far hotter environment than Earth. The star that Kepler-22b orbits is cooler and emits less radiation than our Sun, meaning the planet receives less energy overall. This lower radiation output could affect the planet's temperature distribution, causing its climate to behave quite differently from Earth's. While Earth experiences seasons due to its axial tilt and rotation, Kepler-22b's climate might be driven by factors like the planet's orbit and its rotation period. If the planet rotates slowly, one side could experience perpetual daylight while the other side remains in constant darkness, creating extreme temperature differences between the two hemispheres. Such a climate could make Kepler-22b a place of harsh and unyielding conditions, with the possibility of hostile environments that might not support Earth-like life. Despite these complications, Kepler-22b still holds intrigue as a potentially habitable world. Its location in the habitable zone of its star places it in the right zone to support liquid water, an essential factor for life. However, the risks and challenges posed by its size, atmosphere, and star's radiation output make it a more complex and unpredictable candidate. The planet stands as a reminder of the many uncertainties surrounding the potential for life beyond Earth and the complexities that scientists must navigate as they explore distant exoplanets. As we peer deeper into the cosmos, planets like Corot-7b and Kepler-22b compel us to reconsider the definitions of habitability and life itself. They challenge our understanding of what environments might support life, and demonstrate that the conditions we take for granted on Earth could be the exception rather than the rule in the vast expanse of space. Each discovery, each new exoplanet, holds the promise of expanding our knowledge of the universe, and perhaps one day revealing a world where life can thrive in ways we cannot yet imagine. Until then, the mysteries of planets like Corot-7b and Kepler-22b remind us of the incredible variety of conditions that exist out there, waiting to be explored. Kepler-22b, a planet nestled within the habitable zone of its star, has sparked intense curiosity, primarily due to its potential for hosting life. This zone, the region around a star where temperatures could allow for liquid water to exist on the surface of a planet, was once thought to be the golden criterion for habitability. Yet, Kepler-22b challenges these traditional notions. While it resides within this habitable zone, the exact nature of the planet remains largely unknown, particularly when it comes to its geological composition and atmosphere. Could it resemble Earth with a rocky surface, or might it be dominated by oceanic ice or thick layers of gas? Such variations hold profound implications for the existence of life and its potential to adapt to radically different environmental conditions. The mystery deepens when considering the potential geological features of Kepler-22b. If the planet's surface is rocky, it might have terrain similar to Earth's, offering a familiar yet alien landscape where life could, in theory, thrive. However, if it is instead composed of oceanic ice or enveloped in gaseous layers, the conditions could be drastically different, affecting everything from the planet's climate to its ecosystems. In such cases, life may not only face distinct challenges, but its very structure and metabolism might need to adapt to an entirely foreign set of circumstances. Organisms, if they exist, might rely on energy sources unlike anything we are familiar with on Earth, perhaps harnessing chemical reactions from a unique atmospheric composition or surviving on solar radiation levels far different from our own. Kepler-22b's larger-than-Earth size adds another layer of intrigue. Being classified as a super-Earth, the planet could possess an atmosphere far denser than our own, which might allow it to retain heat more effectively. This characteristic alone could extend its habitable range beyond traditional expectations, opening up the possibility that planets outside of our solar system could harbor life, even if they are significantly larger or have vastly different compositions than Earth. As researchers explore this possibility, they are forced to rethink the rigid boundaries once believed to define a planet's habitability. Moreover, the theories surrounding Kepler-22b's atmosphere have prompted both awe and trepidation. Some scientists speculate that the planet may be shrouded in a thick, dense atmosphere, similar to Venus, with suffocating temperatures and unbearable pressure. If this were true, survival would seem impossible, and the planet might become a cautionary tale about the extreme conditions that can arise in distant corners of the universe. In this scenario, the relentless greenhouse effect could lead to unpredictable and violent weather patterns, potentially making the surface uninhabitable. In contrast, other theories paint a more mysterious picture, suggesting that Kepler-22b could harbor clouds of liquid water or ammonia, creating a dynamic environment where life might be able to survive, but only under the most bizarre of circumstances. This kind of environment could be home to microorganisms that thrive in extreme conditions, creatures capable of withstanding constant storms or surviving in atmospheres rich in hazardous chemicals. Yet, such an atmosphere might also inhibit the emergence of complex life forms, particularly those that rely on Earth-like conditions. Could such an atmosphere hold a biochemistry entirely alien to us, raising the possibility that Kepler-22b either harbors life in an unfamiliar form or is completely devoid of it? This backdrop of uncertainty leads to an atmosphere thick with intrigue and questions. Kepler-22b is both a symbol of hope in the search for life beyond our solar system and a reminder of the potentially harsh realities of exploring other worlds. Its existence forces us to confront our own assumptions about what makes a planet hospitable and to reconsider the many ways life could manifest should it be present. Each new theory surrounding its atmosphere raises critical questions about the resilience of life, its potential to evolve, and the many extremes that nature might take. The discovery of Kepler-22b also marks a pivotal moment in the study of exoplanets. This world was one of the first to be confirmed within the so-called habitable zone, a region of space where conditions might be just right for liquid water, an essential ingredient for life as we know it, to exist on a planet's surface. However, as astronomers study Kepler-22b further, it becomes clear that the concept of the habitable zone is far more complex than originally thought. For instance, Kepler-22b's size and atmosphere suggest that it may retain heat more effectively than Earth, allowing liquid water to exist, even if it is located closer to its star than we had previously imagined would be possible. What makes Kepler-22b particularly fascinating is that it resides in a space between traditional expectations and the realm of possibility. It challenges the assumption that only planets similar in size to Earth are capable of supporting life. Instead, it opens up the possibility that larger worlds, so-called super-Earths, might be able to sustain life in ways we have not yet fully understood. This encourages scientists to expand their definitions of habitability, taking into account a wider range of planetary characteristics, including atmospheric composition, pressure, and stellar radiation. In fact, the findings from Kepler-22b are prompting scientists to reconsider what constitutes the habitable zone altogether. The traditional view was that a planet must be situated in a narrow band around a star, neither too hot nor too cold, for liquid water to exist on its surface. However, Kepler-22b demonstrates that this zone is more dynamic than we previously thought. Factors such as a planet's atmospheric pressure and its composition can have profound effects on its ability to support liquid water, even at the inner or outer edges of the habitable zone. A planet with a thick, heat-retaining atmosphere might remain warm enough to allow for water to flow, even if its orbit is closer to its star than Earth's is to the Sun. This realization opens the door to a broader and more nuanced view of planetary habitability, one that allows for a wider range of possible conditions under which life might exist. At the same time, as astronomers continue to study Kepler-22b, they are coming to understand that habitability is not merely a matter of a planet being in the right place within its star system. It's a more intricate and layered issue, dependent on a multitude of factors that go beyond a planet's distance from its star. This insight is reshaping our approach to the search for life in the universe, encouraging a deeper exploration of the myriad ways that life could adapt in varied environments across the cosmos. Meanwhile, back in our own solar system, the Great Red Spot on Jupiter stands as another testament to the extreme forces at play in planetary weather systems. This colossal storm, which has been raging for centuries, is one of the most powerful and awe-inspiring weather phenomena known to humankind. It is an anticyclonic storm, meaning it rotates in the opposite direction of cyclonic storms on Earth, with winds that are so fierce and sustained that the storm could easily engulf multiple planets the size of Earth within its swirling clouds. This storm is not only a fascinating feature of Jupiter's atmosphere, but also a window into the dynamic and turbulent nature of gas giants. The Great Red Spot is driven by a unique set of atmospheric conditions, including Jupiter's rapid rotation and its thick, gaseous atmosphere. Unlike Earth, which completes a rotation every 24 hours, Jupiter spins much faster, finishing one full rotation in less than 10 hours. This rapid movement generates incredibly powerful winds, which, in combination with the immense heat emitted from the planet's core, create an environment where storms can develop and persist. The Great Red Spot is fed and sustained by this constant influx of energy, and its powerful winds and swirling patterns reflect the immense scale of Jupiter's atmosphere. The storm's vivid reddish hue is another striking characteristic. This coloration is thought to result from complex chemical reactions occurring within the storm's clouds, potentially involving compounds such as phosphorus and sulfur. These reactions contribute to the spot's distinctive appearance, making it a subject of fascination for astronomers and casual observers alike. Yet, as much as the Great Red Spot captivates us, it also serves as a reminder of the immense and often unpredictable power of planetary weather systems, a reminder that the forces of nature in our own solar system are every bit as mysterious and awe-inspiring as those we encounter when looking toward distant worlds like Kepler-22b. The Great Red Spot, one of the most mesmerizing and enduring phenomena in our solar system, stands out not just because of its sheer size, but because of its remarkable longevity. For over 300 years, this enormous storm has been a constant feature of Jupiter's atmosphere, a testament to its strength and resilience. Observations from numerous space missions continually reinforce the storm's remarkable stability. Despite variations in its size and intensity, the Great Red Spot has remained a consistent presence, offering scientists a captivating glimpse into a weather system far beyond the confines of Earth. This storm's persistence is a striking example of Jupiter's atmospheric complexity, and it serves as a living demonstration of the massive, often unpredictable forces at play on the gas giant. While other storms on Earth are temporary, lasting days or weeks at most, the Great Red Spot has endured for centuries, demonstrating an unparalleled degree of longevity. Researchers studying this colossal storm gain insights into the dynamics of planetary weather, providing a new perspective on the complexities of nature's most powerful forces. Jupiter, a gas giant primarily composed of hydrogen and helium, lacks a solid surface, which allows its storms to grow and evolve unhindered by the constraints that exist on rocky planets like Earth. This unique feature of Jupiter's atmospheric dynamics allows massive systems like the Great Red Spot to persist for long periods. The planet's rapid rotation plays a significant role in driving the chaotic weather patterns seen on the gas giant. In conjunction with deep convective currents that pull heat from the planet's interior, these forces combine to create powerful winds that can reach speeds in excess of anything seen on Earth. The resulting weather system is one of swirling clouds and violent lightning, a dynamic interplay of turbulent forces. Jupiter's storms are not just aesthetically impressive, they represent the core of the planet's dynamic nature. The atmosphere itself operates in layers, with different wind speeds and directions at various altitudes, creating intricate interactions between the storm systems. This contributes to unpredictable weather patterns, like the formation of dark cloud bands and contrasting white ammonia clouds. These visual contrasts are not just a captivating display, they reflect the underlying chaos of the planet's weather, constantly shifting and reshaping the atmosphere. The sheer scale and intensity of these storms underline Jupiter's role as the undeniable giant of our solar system. Each storm is a reminder of the violent forces at work on this massive planet. Jupiter's chaotic atmosphere challenges our understanding of planetary systems, illustrating a world where violent storms are not anomalies, but rather the status quo. The beauty of its cloud formations is matched only by the peril inherent in the planet's tumultuous depths, creating a world that is both awe-inspiring and intimidating. In addition to its massive storms, Jupiter's magnetic field is another formidable feature that makes the planet a fascinating yet hazardous place for exploration. Imagine Jupiter as a colossal magnetic dynamo. Its magnetic field is far stronger than Earth's, extending millions of kilometers into space. This immense field creates a vast bubble known as the magnetosphere, which envelops the planet. The magnetosphere traps charged particles from the solar wind and from the planet itself, creating an environment that is both complex and dangerous. As spacecraft venture closer to Jupiter, they encounter this magnetic field, where they are bombarded with high-energy particles and intense radiation. These charged particles are like tiny but destructive missiles, capable of damaging spacecraft. The radiation belts surrounding Jupiter contain particles millions of times more energetic than those found in Earth's radiation belts, posing serious risks to spacecraft, electronics, and any potential human explorers. The region around Jupiter is an incredibly dynamic environment. Magnetic fluctuations can create powerful bursts of radiation, which spacecraft must carefully navigate to avoid damage. Such extreme conditions complicate missions, often making it difficult to collect data or conduct experiments. Every mission to Jupiter requires meticulous planning to ensure that spacecraft can withstand the dangerous forces at play in the planet's magnetic field. Jupiter's role as the largest planet in our solar system adds a sense of awe and trepidation. This gas giant could easily contain more than 1,000 Earths within its massive volume, giving us a tangible sense of just how small our planet is in comparison. But it is not just Jupiter's size that is awe-inspiring. It's the grandeur of its swirling atmosphere, filled with thick bands of clouds and storms that have been raging for centuries. The Great Red Spot, a storm larger than Earth, serves as the most striking example of the planet's dynamic and ever-evolving weather systems. Its sheer scale invites wonder, prompting questions about the complexities of planetary weather systems and the forces that shape them. But as much as Jupiter's size and atmospheric features are fascinating, they are also intimidating. The planet's environment is one of extreme pressure and temperature, conditions that are inhospitable to humans. The gravity on Jupiter is far stronger than that on Earth, meaning that if a person were to land there, they would feel incredibly heavy, with every movement becoming a difficult and exhausting task. Jupiter's unique characteristics, the Great Red Spot, its tumultuous storms, and its formidable magnetic field, together paint a picture of a planet that is both a marvel of nature and a dangerous frontier. The complexity of Jupiter's weather, combined with its immense size and powerful magnetic forces, makes it one of the most extraordinary planets in our solar system. As we continue to explore it, we are reminded that while some of the most incredible natural phenomena are beautiful and awe-inspiring, they also embody the raw, chaotic energy that exists in the universe. Jupiter is not a planet to be tamed, but one that challenges our understanding and reminds us of the vast, untamed forces that shape the cosmos. The planet Jupiter, with its immense size and power, radiates more energy than it absorbs from the sun. This fact hints at the presence of an active, turbulent interior. Beneath the thick layers of clouds, the planet's core generates internal heat, which fuels powerful storms and atmospheric phenomena. The violent weather patterns observed on Jupiter serve as a stark reminder of the dynamic and unpredictable forces that shape the planet, forces that could be capable of unleashing extreme tempests. One of the most striking features of Jupiter is its enormous magnetic field, which is capable of producing intense radiation belts around the planet. These radiation rings pose a significant threat to any spacecraft that ventures too close to Jupiter, as the radiation can be lethal to both human and robotic explorers. Jupiter's magnificence, paired with its inherent dangers, acts as a powerful symbol of the cosmic forces at play in the universe. It challenges our understanding of what is possible in nature and simultaneously highlights our own vulnerability in the vast and unfathomable expanse of space. Turning to Uranus, this planet is exceptional in ways that set it apart from all other planets in our solar system. Its most striking characteristic is its extreme axial tilt. While most planets rotate with their axes roughly aligned to their orbits, Uranus is tilted over so dramatically that it spins almost on its side. The tilt of Uranus is so severe that it is nearly perpendicular to its orbit around the Sun. This unique orientation results in a completely different seasonal experience compared to anything we observe on Earth. As Uranus orbits the Sun, one of its hemispheres is continuously bathed in sunlight for about a quarter of its year, which equates to roughly 20 years on Earth. During this period of constant daylight, temperatures rise, and the atmosphere becomes more active. Winds intensify and dynamic weather patterns emerge. However, as the planet continues its orbit, the same hemisphere that had been basking in sunlight is plunged into a prolonged period of darkness, lasting another 20 years. This dark phase brings with it bitter cold, and the atmosphere grows still, descending into a period of eerie calmness. The stark seasonal changes on Uranus are unlike anything seen on Earth. The dramatic transitions between endless daylight and months of darkness lead to extreme weather patterns, where fierce storms can form and dissipate under the influence of the sun's warmth. When the planet's tilted axis causes the sun to shine directly over its equator during the equinoxes, the weather patterns undergo rapid and sometimes violent changes, resulting in chaotic storms. These transitions highlight the profound connection between a planet's tilt and its atmospheric behavior. The surface of Uranus presents a captivating but desolate landscape. Unlike the rugged, mountainous terrains of Earth or Mars, Uranus appears strikingly featureless. Its atmosphere is composed of thick clouds made primarily of hydrogen, helium, and methane, which give the planet its distinctive blue-green hue. Beneath these clouds lies a frigid, icy crust, which is composed mainly of water, ammonia, and methane ice. The surface of Uranus is smooth and uniform, lacking the geological features such as valleys, mountains, or craters found on other celestial bodies. This makes the planet feel empty, even alien, and contributes to its cold, inhospitable atmosphere. Temperatures on Uranus are among the lowest in the entire solar system. Its distance from the sun leaves the planet dimly lit, further deepening the mystery of its environment. Winds rush through the atmosphere, stirring the clouds, but the ice beneath remains undisturbed, adding to the unsettling stillness of the planet's surface. The planet's unusual tilt only compounds the eerie sensation of isolation. As one hemisphere is bathed in sunlight for decades, the other hemisphere is cast into an endless, frigid winter. This cycle of extreme cold and intense warmth adds to the surreal nature of the planet, making it a world of stark contrasts. Beyond its unique weather patterns, Uranus is also home to a magnetic field that is unlike any other planet in the solar system. The planet's magnetic axis is misaligned with its rotational axis, which results in a magnetic field that does not follow the usual patterns seen in other planets. This irregularity causes Uranus's magnetic field to take on an unusual tilted shape, extending in unpredictable directions and producing fascinating auroras and electric currents within the atmosphere. These magnetic peculiarities, along with its axial tilt, lead to extreme atmospheric phenomena, including intense storms with winds that can reach incredible speeds. The relationship between Uranus's magnetic field and its rotation challenges our understanding of planetary dynamics. Why does the planet possess such an unusual tilt? What caused its magnetic field to develop in such an anomalous way? These questions are central to ongoing research and exploration, and each discovery brings us closer to unraveling the mysteries of Uranus's formation and evolution. Uranus's faint rings further add to its mystique. Unlike the vibrant and striking rings of Saturn, Uranus's rings are subtle and dark, making them difficult to observe. These narrow, dark bands are composed of tiny particles ranging from dust-sized grains to larger boulders. Their faint appearance adds an air of mystery to the planet, as if the rings belong to some forgotten or ghostly part of the cosmos. The discovery of these rings in the early 1980s only deepened the enigma surrounding Uranus. The origin of these rings is still unclear. Some scientists speculate that they could be the remnants of moons that were shattered in ancient collisions, or perhaps the result of gravitational interactions with nearby objects. This possibility hints at a dynamic and violent history for Uranus, one filled with cosmic events that have shaped the planet into what we see today. The very existence of these rings invites us to imagine a past full of dramatic changes and catastrophic events, contributing to the haunting allure of the planet. Ultimately, Uranus is a planet that defies conventional understanding. Its extreme axial tilt, unique magnetic field, and bizarre seasonal changes offer us a glimpse into the strange and varied nature of planetary systems. Every feature of Uranus, from its icy surface to its mysterious rings, contributes to the planet's enigmatic presence in our solar system. It remains one of the most intriguing objects of study in astronomy, a testament to the infinite diversity and wonder that exists within the cosmos. The faintness of the rings surrounding Uranus often leaves them hidden in the vastness of space, making them difficult to detect without the right tools. This subtlety adds a layer of mystery, creating an air of hidden secrets waiting to be revealed. It's this enigmatic allure that draws in researchers and space enthusiasts alike, prompting a fascination with what lies beyond the visible spectrum. When paired with the planet's unique rotation, frigid atmosphere, and bizarre moons, the rings of Uranus contribute to a story that feels as much about the spirit of exploration as it does about the unknown. This sense of wonder and intrigue cements Uranus's reputation as one of the most mysterious and perplexing planets in our solar system. Far beyond the comforting reach of the sun lies Neptune, the distant blue planet known for its tempestuous and tumultuous atmosphere. Here, some of the most violent winds in our solar system tear across its surface, reaching speeds that far surpass anything found on Earth. These winds, reminiscent of powerful storms on a scale all their own, create a unique challenge for scientists attempting to study extreme weather phenomena. The raw power of Neptune's winds, which can exceed the speed of sound, raises compelling questions about the forces that drive them. Unlike on Earth, where solar energy is the primary engine behind our weather, Neptune exists in an area of space far removed from the sun's heat. This leads scientists to speculate: what drives the fierce winds on Neptune? How can weather systems exist in such cold regions where the temperature is much lower than what we experience on our home planet? The answer may lie in previously unknown internal heat mechanisms or in unique atmospheric compositions, phenomena that suggest the weather dynamics on Neptune might operate in ways that challenge everything we thought we knew about planetary atmospheres. The complexity of Neptune's weather only deepens the mystery. While Earth's weather systems are dictated by the planet's rotation and temperature differences, giving rise to cyclones and anticyclones, Neptune's weather seems to follow entirely different rules. The atmosphere of Neptune is a swirling cauldron of clouds composed mainly of hydrogen, helium, and methane, with methane giving the planet its striking blue hue. These elements have a profound impact on how storms form, evolve, and move across the planet. Massive, dark storm systems form, some of which resemble hurricanes, only on a much grander scale. On Earth, storms typically dissipate after a period, transitioning through various phases. But on Neptune, storms can persist for extended periods of time, raising intriguing questions about how energy is conserved and redistributed in such a vast atmosphere. This persistence may suggest that Neptune's atmospheric dynamics are governed by a balance of forces and energies vastly different from what we experience on Earth. This raises the possibility of a new theory about how weather systems could operate on other planets, especially in colder and more distant regions of space. The study of Neptune's extreme weather conditions offers valuable insights not only into the planet's own atmospheric processes, but also into weather systems on other celestial bodies. By expanding our understanding of the weather on Neptune, scientists are able to explore new theories about the nature of planetary atmospheres. These findings could have broader implications for exoplanets like worlds far beyond our solar system that may harbor their own unique weather systems. As scientists continue to study Neptune, each new discovery acts as a vital piece in the puzzle of understanding planetary atmospheres across the universe. In this way, Neptune becomes more than just a distant cold planet. It serves as a model for understanding what constitutes extreme weather conditions on a cosmic scale. One of the most striking features of Neptune's turbulent atmosphere is the Great Dark Spot, a colossal storm that is often compared to the famous Great Red Spot on Jupiter. Stretching over thousands of kilometers, the Great Dark Spot exemplifies the violent nature of Neptune's weather, where intense winds swirl and clash, creating immense waves and chaotic weather patterns. The storm forms as strong winds interact with the deeper, warmer clouds in Neptune's atmosphere, which absorb more sunlight, causing the storm to appear darker in contrast to the lighter gases surrounding it. This dark spot is not a permanent feature. It changes rapidly, sometimes vanishing altogether. It is a dynamic, ever-changing phenomenon that adds to the planet's eerie and dramatic landscape. The persistence and evolution of storms like the Great Dark Spot provide scientists with invaluable data. Unlike storms on Earth, which typically last for a few days or weeks, Neptune's storms can evolve at an entirely different pace. Some of them can even last for years, transforming before our eyes. These changes give researchers a deeper understanding of the meteorological processes at work on Neptune, shedding light on how such extreme weather systems can emerge and persist in a planet's atmosphere. The transformation of the Great Dark Spot serves as a reminder that the forces shaping Neptune's weather are both unpredictable and awe-inspiring, mirroring the untamable nature of the universe itself. Gazing upon Neptune, it is impossible to ignore the striking deep blue color that defines this distant world. The vivid cerulean hue is the result of methane molecules in the atmosphere, which absorb light in the red part of the spectrum while reflecting and scattering blue light. This interaction gives Neptune its iconic blue appearance, one that captivates the human imagination, evoking both awe and wonder. This breathtaking vision draws us into the vastness of space, triggering a sense of both admiration and unease. Despite the serene beauty of its color, Neptune is a world of extremes, where winds whip at unimaginable speeds and storms rage with violent fury. The very qualities that make Neptune visually captivating also highlight its inhospitable nature. Beneath its tranquil surface lies a chaotic and dangerous environment that is unforgiving to any form of life as we know it. The planet's composition, predominantly hydrogen, helium, and methane, forms a thick, oppressive atmosphere where the pressure is immense and the temperatures are frigid. The conditions on Neptune are so inhospitable that life, as we understand it, could not exist there. The temperatures near the cloud tops can plunge to hundreds of degrees below freezing, making it a place far colder than the most extreme winters on Earth. Imagine an environment where the very air is made up of gases that are toxic and unbreathable to any terrestrial organism. This stark contrast between Neptune's surface beauty and the hostile conditions beneath it underscores the duality of exploration, our fascination with the unknown and the beauty that lies in the deepest, most dangerous corners of space. Neptune, with its stunning blue hue and violent atmospheric conditions, reminds us of the infinite complexity of the universe. It symbolizes both the breathtaking beauty and the hidden dangers that lie beyond the limits of human exploration. The mysteries of Neptune, its storms, winds, and extreme conditions, invite us to reconsider what we know about the cosmos. They urge us to expand our understanding of the forces that shape not only the planets in our solar system, but also those in distant star systems as we continue to seek out answers to the questions that have intrigued humanity for centuries. Moreover, the atmospheric pressures on Neptune are overwhelmingly intense. If you were to begin a descent into the heart of this distant planet, you would feel the pressure increase at a staggering rate. As you venture deeper, the force pressing down would escalate far beyond the capabilities of any known life forms to survive. The weight of the atmosphere would grow unbearable, creating an environment where even the most resilient organisms from Earth would stand no chance. In addition to these crushing pressures, Neptune is home to some of the most violent storms in the entire solar system. Winds on this planet can reach speeds far greater than even the strongest hurricanes recorded on Earth. These relentless winds swirl through Neptune's atmosphere, creating a chaotic dance of clouds and storm systems. The weather here is a spectacle of ferocity, violent, unpredictable, and dangerous, but the brutality of Neptune's environment doesn't stop there. The atmosphere of the planet contains large amounts of methane, a gas that is often discussed in the context of its potential as an energy source. However, on Neptune, methane plays a very different role. The planet's atmosphere is composed of a mix of gases that make it unsuitable for supporting life as we understand it. Unlike Earth's life-sustaining atmosphere, Neptune's air lacks the essential compounds and elements required for organisms to thrive. The combination of methane, cold, unbreathable gases, immense pressure, and turbulent weather patterns creates a world where survival is inconceivable. On Neptune, the extreme cold and volatile weather presented a nearly insurmountable barrier to life. This is not just a place where life is unlikely to exist. It is a world where life as we know it find no purchase. The conditions are so far removed from the nurturing environment of Earth that even the most robust forms of life could not survive. In contrast, on the exoplanet GJ 436b, located approximately 42 light-years from Earth, there exists a strange and frightening phenomenon known as burning ice. This planet, orbiting a star much smaller and cooler than our Sun, has atmospheric conditions that create a form of water that is entirely alien to us. Rather than existing as the familiar liquid we know, water on GJ 436b takes on a bizarre state, transitioning from solid to a unique form of liquid that behaves very differently from the water on Earth. At such high temperatures and pressures, water on this exoplanet does not simply melt, it burns. The phenomenon of burning ice on GJ 436b introduces a host of potential hazards as the planet's intense heat and pressure push substances to their limits. This altered state of water could result in chemical reactions that produce gases or materials unlike anything found on Earth. These reactions might create toxic clouds or surface conditions that are utterly inhospitable, further sealing the planet's status as a hostile environment for any form of life. In addition to this strange state of water, the extreme temperatures and the resulting chemical instability could lead to unforeseen atmospheric reactions, creating volatile environments that only add to the planet's inhospitable nature. The violence of the weather, driven by the relentless heat, combined with the potential for tidal forces and storms, creates a setting where survival would be nearly impossible. The very landscape of GJ 436b paints a picture of an alien world far removed from Earth's familiar terrain. The ice that burns, the scorching temperatures, and the volatile atmospheric conditions all combine to form a world so radically different from our own that it challenges our understanding of what a planet can be. In such an environment, life as we know it would face insurmountable obstacles. This extreme case of an exoplanet provides a stark scientific study of planetary dynamics, particularly due to its unusual gravitational interactions. GJ 436b's proximity to its host star is a crucial factor in shaping its extreme conditions. The planet orbits a star that is much smaller and cooler than our Sun, yet it has a remarkable density, suggesting it is composed largely of water in a state that defies earthly understanding. The planet's intense gravitational pull caused by its close orbit causes enormous pressure to build up on the water that makes up much of its composition. The result is a situation where water, compressed by gravity, behaves like ice but with the properties of a liquid, forming what can be described as hot ice. The combination of this extreme pressure and the intense heat from the nearby star creates an environment where strange weather phenomena abound. The winds are fierce and ceaseless, constantly whipping across the planet, as the warped pressure conditions lead to storms that could dwarf even the most extreme weather events we experience on Earth. The surface of GJ 436b is a harsh landscape, constantly buffeted by the forces of nature, and the atmosphere is in constant turmoil. In this alien environment, the chemical composition of the atmosphere plays a critical role. The gases that make up the planet's air are far from the life-sustaining mixture we are familiar with on Earth. The high temperatures, combined with the overwhelming pressure, create conditions that would be lethal to any organism from Earth. The thick atmosphere traps the heat, leading to an exaggerated greenhouse effect that forces surface temperatures to soar to levels that would be unmanageable for any known form of life. The planet's status as a hot Neptune provides some insight into its extreme nature. This type of planet, with its gaseous atmosphere and close orbit to its star, is similar to Neptune in our solar system, but far more extreme. The immense pressure and heat on GJ 436b are the result of both its close proximity to its star and the density of its atmosphere. This creates a locked cycle of oppressive heat and pressure, which continually intensifies as gases trap heat within the planet's atmosphere, further exacerbating the hostile conditions. This combination of extreme temperature, crushing pressure, and toxic atmospheric composition makes GJ436b a prime example of an uninhabitable exoplanet. Life, as we know it, could never take root in such an environment. The planet's incredibly harsh conditions ensure that, should any form of life have evolved on GJ436b, it would face extreme challenges and likely be wiped out by the planetary forces at play. GJ436b is a fascinating case study, one that pushes the boundaries of our understanding of exoplanets and planetary science. With its molten surface, brutal weather systems, and its status as a hot Neptune, this distant world is a stark reminder of how varied and extreme the conditions in our universe can be. While Earth provides the ideal conditions for life as we know it, GJ436b serves as a cautionary example of the dangers that can exist on planets that orbit distant stars, where survival would be nearly impossible for any known life form. The extraordinary pressures, intense heat, and volatile weather patterns ensure that this planet remains an inhospitable wasteland, a world where the very concept of life is difficult to even imagine. The planet LHS 1140b stands as a unique and perplexing anomaly in the ever-expanding universe of exoplanets. A fascinating blend of extreme conditions, this world harbors mysteries that challenge our understanding of planetary formation, chemistry, and the very nature of life itself. While the planet's exterior suggests heat, its interior holds unexpected surprises, such as pockets of ice. This is a phenomenon that should not be possible under such intense heat, creating a paradox that has caught the attention of scientists worldwide. The coexistence of such contrasting elements, ice and fire, occurs due to the immense pressure deep within the planet's core, where water is transformed into a form of ice unlike anything we experience on Earth. The pressure is so great that it alters the behavior of water, creating conditions that are entirely alien to us. The discovery of this strange coexistence has led scientists into deep inquiry, attempting to decipher how such conditions can exist side by side. Questions arise about the chemical reactions occurring within the planet's depths, the material properties under extreme pressure, and the limitations of planetary science itself. The idea of a planet where both ice and fire can thrive stirs not only wonder, but also a fearful curiosity among researchers. This strange duality defies standard planetary formation theories, forcing scientists to reconsider what is possible on other worlds and what forms of life, if any, could exist in such an environment. The mystery of LHS 1140b compels researchers to delve into the unknown, challenging them to expand their theories about the diverse and exotic conditions that might exist elsewhere in the universe. These extreme conditions raise even more profound questions. What types of chemical processes could occur in this hostile environment? Could there be unknown processes at work beneath the surface, ones that could reveal entirely new forms of chemistry? Each question serves as a key to unlocking the mysteries of this enigmatic world, opening the door to new scientific theories and deeper explorations of the universe. LHS 1140b, with its ice and fire duality, offers a glimpse into a new realm of possibilities, making it a prime candidate for researchers interested in understanding both the nature of planets and the fundamental building blocks of the universe itself. Further complicating the study of exoplanets is LHS 1140b's proximity to its host star. Orbiting a red dwarf star, this planet faces extreme environmental conditions as a result of its close distance to the star. While red dwarf stars are smaller and cooler than our sun, they still emit enough radiation to have a significant impact on a planet's atmosphere and surface. LHS 1140b, with its close orbit, is bathed in intense stellar radiation which drastically raises its surface temperature. The amount of heat the planet receives can fluctuate greatly depending on its rotation and the nature of its atmosphere. If the planet has a thick atmosphere, it could trap the heat, creating a runaway greenhouse effect, much like what we observe on Venus. However, the exact effects on LHS 1140b remain unknown, adding an element of unpredictability to the planet's climate. The red dwarf star itself also presents an additional challenge for LHS 1140b. Red dwarf stars, including the one that LHS 1140b orbits, are prone to emitting powerful stellar flares, massive bursts of radiation that can have catastrophic effects on nearby planets. These flares can strip away a planet's atmosphere, making it incredibly difficult for life to thrive in any form that we recognize. The combination of the planet's close orbit and the erratic nature of its host star creates a volatile environment, one filled with intense radiation, the potential loss of atmosphere, and extreme temperature swings. Such conditions make it clear that life, if it exists on LHS 1140b, would have to endure extreme and constantly changing forces. However, despite these harsh conditions, the study of LHS 1140b offers essential insights into the broader landscape of exoplanets and planetary science. As scientists seek to understand more about this planet, they are learning valuable lessons about planetary atmospheres, the dynamics of extreme radiation, and how these factors shape a planet's surface and its potential for supporting life. LHS 1140b, with its hostile conditions, serves as a window into the unknown, offering clues about how planets evolve and how life, if it exists, could survive in extreme environments. LHS 1140b's atmosphere adds another layer of intrigue to its already complex nature. Classified as a super-Earth, this planet is larger than our own, yet it may still possess the capability of retaining a significant atmosphere. The density of this atmosphere raises profound questions about what gases it might contain, and whether these gases could support life in any form. In many ways, the planet's atmosphere acts as a delicate balance between the potential for life and the danger of inhospitable conditions. The presence of gases such as oxygen and nitrogen, elements essential for life, could signal that LHS 1140b might support some form of life. On the other hand, the sheer density of the atmosphere could indicate a much harsher reality. Extreme pressure, intense heat, and an atmosphere rich in greenhouse gases like carbon dioxide, which could turn the planet into a scorching furnace, uninhabitable for any known form of life. The atmosphere of LHS 1140b also raises questions about weather systems and climate. If the planet has a thick, dense atmosphere, it could generate clouds, storms, and weather patterns, much like what we experience on Earth. This could suggest that LHS 1140b experiences complex climatic systems, possibly similar to those on Venus or Earth, but on a much more extreme scale. Understanding the atmospheric conditions on such a planet could provide crucial insights into planetary formation, the dynamics of climate systems, and the potential for life on other worlds. On the other hand, the dense atmosphere might also present significant obstacles to human exploration. The pressure on the planet could be so extreme that any familiar organism, including humans, would be crushed under the weight of the atmosphere. Such conditions would make it nearly impossible for any form of life from Earth to survive on its surface. While these challenges make LHS 1140b a fascinating target for scientific inquiry, they also serve as a reminder of the formidable difficulties posed by exploration in such extreme environments. As we continue to explore the universe, the study of planets like LHS 1140b will serve as a critical tool for addressing some of the most fundamental questions about life beyond Earth. These questions include how atmospheres evolve, what they can reveal about a planet's history, and whether the search for life will one day lead us to worlds that are both fascinating and terrifying in equal measure. LHS 1140b, with its unique blend of heat, pressure, and potential for complex chemistry, offers us a compelling window into the future of space exploration. Whether it is ultimately found to harbor life or not, it continues to challenge our perceptions of what is possible in the universe and forces us to reconsider the ways in which life might exist in the most extreme environments. Ultimately, LHS 1140b is more than just another exoplanet. It is a symbol of the endless possibilities and dangers that await us in the vast, uncharted territories of space. It stands as a testament to both the ingenuity and the humility required in the pursuit of understanding alien worlds, and perhaps, in the end, our own place within the cosmos. The atmosphere of a planet plays a fundamental role in shaping its habitability. If LHS 1140b possesses the thick, dense atmosphere, it could provide the crucial protection needed to maintain liquid water by preventing rapid evaporation. Such an atmosphere could also regulate temperatures, creating a stable environment that could be conducive to life. On the flip side, if the atmosphere is thin or insufficient, the planet may be exposed to extreme conditions, harsh radiation from its star, fluctuating temperatures, and a lack of protection against the vacuum of space. In such a case, any water on the planet's surface could quickly boil away or freeze, leaving the conditions unsuitable for life to emerge or persist. The atmosphere, therefore, becomes a key factor in determining whether the planet could sustain life. Together with LHS 1140b's size, this consideration fundamentally reshapes how we think about the potential for habitability. Instead of focusing exclusively on Earth-like planets, which typically require a similar size, composition, and atmospheric conditions, this new perspective allows us to reconsider a wider variety of worlds, ones with different sizes, compositions, and characteristics. By doing so, we open the door to a broader understanding of habitability, one that includes rocky planets of various dimensions and environments that could harbor life, even if they don't mirror the conditions we are familiar with on Earth. This shift challenges us to expand our definition of what makes a world habitable and shows that life could be possible in places far beyond the narrow parameters we've established from studying our own solar system. In this reimagined search for life, LHS 1140b stands out as a particularly intriguing candidate. Located within the habitable zone of its parent star, this exoplanet resides in a region where conditions could potentially support liquid water, an essential ingredient for life as we know it. However, what makes LHS 1140b especially fascinating is its size and mass. These characteristics are generally associated with environments that would be considered hostile to life, yet LHS 1140b breaks this mold. Unlike the majority of exoplanets discovered within habitable zones, which are often similar in size to Earth and classified as super-Earths or smaller, LHS 1140b is a larger, rocky planet. Its composition suggests that it may contain denser materials, which could lead to a more challenging environment for life to thrive. In fact, the planet's substantial gravitational pull might contribute to the formation of a thick atmosphere, potentially rich in greenhouse gases. Such an atmosphere could trap heat, raising the temperature of the planet to levels that might be inhospitable for most life forms. In addition, LHS 1140b's proximity to a red dwarf star, a type of star known for having much lower luminosity than our Sun, raises additional questions. Because red dwarfs are cooler, their habitable zones are much closer to the star, which means planets like LHS 1140b would need to be in close orbit to avoid freezing temperatures. This proximity, while offering the potential for liquid water, also brings new challenges as it places the planet in a delicate balance where it could be at risk of excessive radiation and flare activity from its star. Red dwarf stars, in particular, are prone to violent stellar flares and bursts of radiation, which could bombard any nearby planets, potentially disrupting their atmospheres and creating hostile conditions for life. Such radiation could harm the stability of LHS 1140b's surface conditions, making it difficult for the planet to maintain an atmosphere that might protect its potential habitability. These factors lead researchers to question whether LHS 1140b can sustain stable surface conditions or whether it is continually bombarded by extreme stellar activity. Nevertheless, despite the complexities of these extreme conditions, LHS 1140b offers an exciting opportunity to challenge existing paradigms about exoplanet formation and habitability. Its unusual features may force us to reevaluate our assumptions about which worlds are capable of supporting life and what the true parameters of habitability are. By continuing to study LHS 1140b, scientists are exploring the very boundaries of what it means for a world to be habitable, reshaping our understanding of the potential for life in the universe. Meanwhile, Kepler-69c presents another intriguing example of how the search for habitable planets continues to challenge our expectations. Unlike many exoplanets, Kepler-69c's orbital characteristics are not typical. While it orbits a star similar to our Sun, its path is far from circular. Instead, it follows an eccentric orbit, causing it to fluctuate in distance from its star as it moves along its path. This eccentricity adds a layer of complexity to the planet's seasonal variations, causing the amount of sunlight it receives, and, by extension, the temperature, to shift dramatically as it moves closer to or farther from its star. As Kepler-69c nears its star, it could experience intense heat, while during its distant points, the climate may cool significantly. This uneven distribution of sunlight leads to a unique climate system that would be hard to predict. In addition to orbital eccentricity, the planet's axial tilt could also play a critical role in its seasonal changes. If the planet's tilt is significant, similar to Earth's, it would create seasons where certain regions face the star more directly at specific points in its orbit, leading to periods of intense heat. Conversely, during other parts of its journey, these same regions could experience long periods of darkness and much cooler temperatures. This combination of an eccentric orbit and axial tilt results in a planet with extreme seasonal fluctuations, where temperatures may swing from blistering heat to freezing cold within short periods. Such rapid shifts could make the planet's climate unpredictable, potentially creating a volatile environment that would challenge any life forms attempting to survive there. Kepler-69c's climate, shaped by this eccentric orbit and axial tilt, would likely be a dynamic and turbulent one, where weather patterns could be chaotic. This could lead to intense storms or even other unusual atmospheric phenomena, making it a planet where understanding the climatic conditions would be both essential and exceedingly difficult. It provides a glimpse into what life might be like on a world where environmental conditions are far from stable, where the planet's very movement through space contributes to dramatic shifts in its climate and weather systems. At a distance of over 250 light-years from Earth, Kepler-69c is not just a scientific curiosity, but a challenge to our ability to study it in detail. The vast expanse of space means that even the most powerful telescopes can only provide us with limited glimpses of its features. These indirect observations, while valuable, cannot offer the kind of depth and clarity that would allow scientists to draw definitive conclusions about its atmosphere, surface conditions, or the possibility of life. Adding to this challenge is the inability to send spacecraft to the planet, a limitation that means we can only rely on the data gathered from afar. This distance creates a barrier to comprehensive research, and yet it also fuels a sense of awe and wonder. The mystery surrounding Kepler-69c, as with many other exoplanets, stirs both excitement and a sense of fear. The potential for discovering new forms of life or ecosystems in such distant regions of space is both inspiring and unsettling. The unknowns surrounding Kepler-69c and exoplanets like it provoke curiosity, but also unease. What if the conditions on these distant worlds are vastly different from anything we can imagine? What if they harbor dangers or threats that we cannot yet comprehend? The tension between the drive to explore and the apprehension about the risks inherent in exploring the unknown is a defining feature of humanity's relationship with space. Our quest to understand the universe is driven by an insatiable desire for knowledge, tempered by the realization that venturing into the unknown comes with inherent vulnerabilities. Kepler-69c stands as a testament to both the promise and peril of space exploration. The great distance between us and this world underscores the limits of our knowledge and the immense challenges we face in our pursuit of understanding distant exoplanets. Yet, it also highlights the enduring fascination we feel when faced with the possibilities that lie beyond our current grasp. As we continue to study Kepler-69c and other exoplanets, we move closer to unlocking the mysteries of the universe. Even as we confront the challenges posed by the vastness of space and the unpredictable nature of the worlds we seek to understand. Kepler-69c and TRAPPIST-1e are two distant exoplanets that have captured the imagination of astronomers and astrobiologists alike. They both sit within the habitable zones of their respective stars, making them prime candidates in the search for extraterrestrial life. Yet, the potential for life on these planets is tempered by profound dangers and uncertainties that challenge our understanding of what it means for a planet to be truly habitable. Kepler-69c, classified as a super-Earth, presents a world where the sheer mass and size of the planet could provide it with the necessary gravity to maintain a thick, life-supporting atmosphere. Such an atmosphere could be rich in essential gases like oxygen and carbon dioxide, both of which are crucial for sustaining life forms similar to those on Earth. If liquid water exists on the surface, it could flow in oceans or lakes, potentially fostering life in environments remarkably like those we find on our own planet. The possibility of such a world stirs up excitement in the quest for extraterrestrial life. The conditions could even mirror those of early Earth, with suitable temperatures and the potential for complex ecosystems to develop. However, this tantalizing potential is paired with significant dangers that make habitability uncertain. The planet orbits a K-dwarf star, which, though stable, is known for emitting bursts of radiation and solar flares. These energetic outbursts could strip away the atmosphere of Kepler-69c over time, rendering it inhospitable. Such radiation could erode the planet's protective layers, leaving its surface vulnerable to harmful cosmic rays and extreme weather conditions. Furthermore, the composition of the planet's atmosphere remains unknown. If the atmosphere is too thick or lacks the right balance of gases, it could be suffocating rather than life-sustaining. Even if liquid water exists, the unsteady conditions of the atmosphere and the fluctuations in temperature and radiation could make it difficult for life to emerge and thrive. Another uncertainty about Kepler-69c is its surface conditions. The planet's geology might be marked by extremes, driven by the strong gravitational forces acting on it. These could create volatile terrain with shifts in the surface that might be too hostile for any form of life to endure. If the planet's temperature varies drastically between day and night, or if intense geological activity disrupts the environment, survival could become a matter of chance rather than certainty. The potential for life on Kepler-69c is as much about what we don't know as what we do. Its proximity to the habitable zone and the possibility of a life-supporting atmosphere should not overshadow the potential risks that accompany its unknown factors. The story of Kepler-69c is one of both hope and peril, a reminder that the universe, while filled with possibility, is equally full of uncertainties. In the case of TRAPPIST-1e, the circumstances are equally tantalizing and fraught with challenges. This planet orbits a small, cool star known as an ultra-cool dwarf in a region where liquid water could exist, critical for life as we understand it. Like Kepler-69c, TRAPPIST-1e sits within the habitable zone of its star, a sweet spot where temperatures could allow for the presence of liquid water on its surface. However, the orbital dynamics of the planets in the TRAPPIST-1 system create a unique and somewhat precarious situation for TRAPPIST-1e. The 7 planets in the system are locked in a gravitational ballet, each one's orbit affecting the others. This causes them to fall into resonant orbits, meaning the planet's orbital periods are closely linked and their movements influence each other in a dramatic way. For TRAPPIST-1e, this means that its orbit could be unstable, altered by the gravitational pull of its neighboring planets. Over time, this instability could lead to changes in its climate, making the conditions unsuitable for life to take root. To make matters worse, TRAPPIST-1e's proximity to its ultra-cool dwarf star exposes it to intense stellar flares, which are bursts of radiation that could strip away the planet's atmosphere. Without a significant magnetic field to protect it from these stellar winds, something that larger planets often possess, TRAPPIST-1e could be exposed to the full force of its star's radiation. This constant bombardment could erode its atmosphere over time, eventually rendering the planet barren and inhospitable. Even if the planet does have liquid water, these powerful cosmic forces could prevent it from sustaining life. In addition to the dangers posed by its stellar environment, TRAPPIST-1e's status as a tidally locked planet presents further challenges. One side of the planet constantly faces the star, while the other remains in perpetual darkness. This results in extreme temperature differences between the two sides. The sunlit side, bombarded by radiation from its ultra-cool star, could experience relentless heating, potentially stripping away any atmosphere and rendering the surface uninhabitable. Meanwhile, the dark side would be plunged into a deep, unyielding cold, creating conditions that could be equally inhospitable. The stark divide between light and dark could lead to extreme climate conditions that may be too harsh for even the most resilient life forms to endure. Despite the potential for liquid water and a habitable environment, the challenges posed by TRAPPIST-1E's orbital dynamics, exposure to intense radiation, and the extreme temperature fluctuations between its two hemispheres make it a highly hostile world for life. The fascinating yet eerie features of this exoplanet serve as a reminder that the search for extraterrestrial life is fraught with complexity. The allure of finding a world that could resemble our own, with the potential for liquid water and an Earth-like atmosphere, is tempered by the harsh reality that such a world might be far more hostile than we can imagine. Both Kepler-69c and TRAPPIST-1E show us that the search for life beyond Earth is as much about confronting the unknown as it is about discovering the possibilities. These planets, with their Earth-like qualities and dangerous unknowns, embody the dual nature of space exploration, hope and peril intertwined. As we continue to study these distant worlds, we learn not only about their potential for supporting life, but also about the intricate balance of factors that make a planet truly habitable. Each discovery, whether promising or disheartening, brings us closer to understanding the vast and mysterious universe we inhabit, shaping our understanding of what it means to seek life beyond our own world. The TRAPPIST-1 system, home to 7 Earth-sized planets, stands as a remarkable mystery in the vast expanse of our universe. With its low-mass star casting a faint light over its planetary neighbors, it invites both wonder and wariness from scientists and astronomers alike. Among these 7 worlds, one in particular, TRAPPIST-1E, captivates the imagination with its potential for supporting life. However, this potential comes with complexities and dangers that challenge our understanding of habitability and survival in extreme environments. The first and perhaps most obvious challenge comes from the gravitational influence of neighboring planets within the TRAPPIST-1 system. These planets, orbiting a star much cooler than our Sun, can exert tidal forces on one another, introducing an unsettling level of volatility. Such gravitational effects could cause significant atmospheric and geological changes, rendering the environment far from stable. The changes might include shifts in the atmosphere, intense geological activity, or even erratic weather patterns, each of which would make the planet's surface more hostile for life as we know it. Yet, despite the terrifying implications of these forces, the volatility could also be seen as a frontier for scientific exploration. The challenges they pose are not merely obstacles, but opportunities to expand our knowledge of life's adaptability. Scientists are eager to explore how life might respond to such conditions, how organisms might evolve to thrive under pressure from intense radiation or erratic climates. This research could unlock secrets about the resilience of life itself, shedding light on the possibility of organisms surviving in environments far more extreme than those of Earth. TRAPPIST-1E, with its extreme environment, beckons us to reconsider the boundaries of what is habitable. It is an invitation to challenge our assumptions and explore whether life could exist in places we would normally deem inhospitable. By studying such planets, researchers aim to push the very limits of biology and astrobiology, redefining the boundaries of life and expanding the universe of possibilities for life beyond our planet. The concept of interplanetary exchanges within the TRAPPIST-1 system adds another layer of fascination, drawing attention to the intriguing potential for communication, travel, and even cooperation between these 7 worlds. Such possibilities fuel dreams of discovering new forms of life, advanced technologies, and ecosystems teeming with the unknown. If these planets do indeed harbor life, then perhaps they could become hubs of collaboration among intelligent beings, working together in shared pursuit of knowledge, peace, and progress. However, the optimistic vision of interplanetary cooperation also stirs a sense of caution and fear. The universe, after all, is an unpredictable place, and the reality of interplanetary relations might not reflect our utopian ideals. There is the potential for societal conflict, resource competition, and even cultural misunderstandings, which could escalate tensions and disrupt any hope of peaceful coexistence. The possibility of disease spreading from one planet to another, pandemics that could wipe out entire populations without defenses, further adds to the risk. With so much at stake, the moral implications of interacting with potentially sentient beings are bound to be significant. Would humanity act with benevolence, Or would it act out of fear or domination? These concerns highlight the dual nature of exploration in the TRAPPIST-1 system. On one hand, there is the allure of making contact with alien life and discovering novel forms of existence. On the other hand, there is the fear of unintended consequences, of triggering conflicts, or even discovering aspects of ourselves we would rather not confront. This duality, the tension between hope and fear, between discovery and danger, forms the core of our fascination with this distant star system as we ponder our place in the galaxy and the broader universe. As we turn our attention back to TRAPPIST-1e, its appeal is not just based on its size or position within the habitable zone of its star, but also on its intriguing similarity to Earth. It is an Earth-like world orbiting a cool dwarf star, sitting within the star's habitable zone, where temperatures might allow liquid water to exist on its surface. Liquid water is, of course, the key ingredient for life as we understand it, making TRAPPIST-1e a tantalizing prospect for further investigation. Its size and composition suggest it might have a rocky surface similar to Earth's, and simulations suggest that it could retain an atmosphere that might allow life to thrive. Yet this promise of habitability is tempered by the harsh conditions it faces due to its proximity to its parent star. Being so close to its star could subject TRAPPIST-1e to intense radiation, tidal forces, and other environmental stresses that might strip away its atmosphere over time. Despite these challenges, scientists are determined to explore whether life might somehow adapt to such extreme conditions, just as some organisms on Earth have learned to survive in seemingly inhospitable environments. The ongoing study of TRAPPIST-1e is not only a quest to understand this planet, but also a deeper investigation into how life might evolve and survive under conditions very different from our own. Simultaneously, the search for potentially habitable exoplanets leads us to consider the possibilities of other worlds like Kepler-62f, an exoplanet that also offers a tantalizing glimpse into the mysteries of alien oceans. Kepler-62f, a planet orbiting a cool star, has been identified as a potential oceanic world, with the possibility of vast bodies of liquid water beneath a thick atmosphere. The promise of rich ecosystems thriving beneath the surface of alien oceans excites scientists and dreamers alike, offering the potential for discovering entirely new forms of life. However, the excitement of exploring such oceanic worlds is tempered by the daunting challenges posed by the extreme conditions found on these planets. For example, the oceans of Kepler-62f might be subjected to pressures equivalent to the crushing depths of Earth's Mariana Trench, making exploration incredibly difficult. Robotic probes and even human missions would have to withstand enormous pressures and potentially harsh chemical environments. Furthermore, the composition of the water could be drastically different from Earth's oceans, containing toxic compounds or corrosive elements that would add another layer of risk to any exploration efforts. Beyond these physical challenges lies the unpredictable nature of the planet's climate. Alien weather patterns could result in violent storms that obscure visibility and make it impossible to study the planet's oceans. The potential for discovering life in such an environment is both thrilling and dangerous. Could life on these distant worlds be radically different from anything we know? What would alien biology look like in an environment where sunlight is scarce and the ocean depths are vast and inhospitable? The quest to understand these oceanic worlds, including Kepler-62f, invites both excitement and fear. It challenges our understanding of the universe and expands the boundaries of what is possible in terms of life and survival. By exploring these worlds, we may uncover new biological principles, new chemical processes, and perhaps even new ways of thinking about life itself. The exploration of alien oceans could rewrite our understanding of biology, chemistry, and the fundamental conditions necessary for life. Yet, even as we dream of these discoveries, the risks cannot be ignored. The technological innovation required to explore these distant and extreme environments would be immense, demanding new breakthroughs in space exploration, material science, and robotics. The possibility of failure, of losing probes or missions to the hostile conditions of these alien worlds, is ever present. However, this very uncertainty, this combination of peril and promise, is what makes the pursuit so compelling. Kepler-62f, like TRAPPIST-1e, stands as a symbol of humanity's ceaseless drive to explore, understand, and perhaps one day make contact with life beyond Earth. The faint sunlight reaching Kepler-62f from its distant star provides yet another layer of complexity. The star, a K-dwarf, is cooler and smaller than our Sun, meaning that the light on Kepler-62f is dimmer and less energetic. Imagine being in a dimly lit room compared to the bright sunlight we experience on Earth, and you begin to understand the challenge of survival on this distant world. Life on Kepler-62f would have to adapt to much weaker light levels, which could make photosynthesis, so essential to life on Earth, much more difficult. Plants or plant-like organisms might need to develop special pigments to absorb whatever light they can. But even such adaptations might have their limits. Additionally, the faint sunlight would likely lead to cooler temperatures, and if the planet's atmosphere isn't thick enough to trap heat, the result could be an environment that is much colder than Earth. These conditions make life on Kepler-62f highly unlikely, or at least very different from what we are accustomed to. Yet, as with all things in science, the improbable can sometimes be the most exciting. The exploration of planets like Kepler-62f and TRAPPIST-1e holds the promise of uncovering not just new worlds, but new ways of thinking about what life is and where it can exist in the universe. As we continue our search for life beyond Earth, these distant planets stand as both challenges and beacons of possibility, urging us to venture further and deeper into the cosmos in the quest to understand our place within it. The faint light that reaches Kepler-62f would have profound effects on its ecosystem, dramatically altering the delicate balance of life. With such limited energy available, the simplest organisms may struggle to extract enough resources, ultimately leading to fewer nutrients for the more complex life forms that depend on them. This could create a world in perpetual twilight, a place where sustaining energy, warmth, and the complex interactions necessary for flourishing would pose significant challenges. The prospect of life on Kepler-62f seems both intriguing and daunting, as the limited energy from its distant sun could spell a harsh existence, severely restricting the evolution of its inhabitants. Kepler-62f orbits within the habitable zone of its star, making it an exciting subject for scientific study. Located approximately 1,1200 light-years from Earth, this exoplanet sparks the imagination with its potential for harboring an environment that could support life. Its size, larger than Earth, raises intriguing questions about the composition of its atmosphere and the conditions on its surface. Could this distant world possess an atmosphere thick with water vapor or gases essential for life as we know it? Or could it be home to clouds of mysterious origins, their composition unknown, creating an environment that is as unsettling as it is fascinating? The possibility of thick clouds enveloping the planet suggests a hidden world, one whose surface features remain obscured. For astronomers, this presents an exciting yet frustrating challenge. What lies beneath the fog? How can we understand the geography and geological processes of a planet that refuses to reveal its secrets? These unanswered questions only deepen the allure of Kepler-62f. If its atmosphere is rich in carbon dioxide, the planet might experience a runaway greenhouse effect, raising temperatures to levels that would make its surface inhospitable. Conversely, if its climate is frigid, water might be frozen, severely limiting the potential for life. Kepler-62f stands as a planet wrapped in mystery, its atmosphere a key to understanding its potential for sustaining life. The uncertainty surrounding its environmental conditions, its atmospheric pressure, its temperature, and its composition creates a narrative of dualities. The planet might hold the promise of discovering life beyond our world, but it also reminds us of the harsh realities of space exploration. This juxtaposition of hope and caution fuels the imagination of scientists and enthusiasts alike, propelling humanity's quest for knowledge deeper into the unknown. The search for exoplanets, such as Kepler-62f, represents a thrilling leap into the cosmos where possibilities seem endless. The dream of discovering alien life is not without its risks, however. Kepler-62f's larger size presents additional questions. A thick atmosphere could intensify the greenhouse effect, pushing temperatures far beyond human tolerance. On the other hand, a thin atmosphere would expose the surface to the unfiltered cold of space, leading to harsh, inhospitable conditions. These uncertainties make it difficult to determine whether Kepler-62f is a place worth exploring or a hostile environment too dangerous to colonize. In this sense, Kepler-62f encapsulates the heart of exoplanet exploration, the delicate balance between hope and apprehension. It represents the thrilling prospect of discovering life in the universe, but also highlights the potential for danger and the unforeseen challenges that might arise from harsh environments. The planet's complex nature is a constant reminder of the unpredictable nature of space, where every discovery brings with it new questions and unexpected complications. As exoplanet hunters push further into the depths of space, they are driven by the promise of Kepler-62f, a promise that is tempered by the harsh realities of what such a discovery might entail. In contrast, Saturn, the majestic gas giant that dominates our solar system, presents a similarly dualistic nature. Its awe-inspiring beauty veiled by the violent weather systems that churn beneath its atmosphere. The most striking feature of Saturn is its intricate system of rings, which sets it apart from all other planets in the solar system. These rings are composed of countless tiny ice particles and dust, creating a dazzling spectacle that captivates the eye of any observer. The complexity of Saturn's rings, with their varying distances and speeds, changes over time due to gravitational interactions, offering a dynamic visual display that adds to the planet's otherworldly allure. Yet beneath this captivating exterior lies a tumultuous atmosphere. Saturn's weather systems are fierce and unpredictable. The planet experiences intense storms with winds that can reach astonishing speeds. Some of these storms are so vast that they rival the size of entire continents, and the lightning strikes that accompany them are millions of times more powerful than those on Earth. The planet's atmosphere is divided into distinct bands, each shifting in color and intensity, revealing a world in constant motion. This combination of beauty and chaos gives Saturn its enigmatic quality, its serene exterior masking the raw, uncontrollable power of its weather systems. Perhaps the most fascinating atmospheric feature of Saturn is the hexagonal storm that lies at its north pole. Imagine a colossal, swirling mass of clouds forming a perfect six-sided shape that stretches across thousands of kilometers. This extraordinary phenomenon is the result of powerful jet streams, where winds can reach speeds that exceed 1,000 miles per hour. As these winds collide, they create the distinct hexagonal pattern that remains stable over time. Unlike many storms on Earth, which tend to dissipate or change shape, Saturn's hexagon has remained in place for decades, perhaps even centuries. This stability suggests a unique balance of forces within the planet's atmosphere, making it one of the most mysterious and intriguing features in our solar system. The sheer size of Saturn's hexagonal storm is mind-boggling. The pattern could easily encompass several Earths within its borders, its size only adding to the sense of awe that it inspires. And while the hexagon itself is a marvel, it is not a solitary feature. Surrounding it are other storms, many of which erupt suddenly and violently, adding to the planet's already tumultuous weather patterns. These storms, in combination with the hexagonal structure, create a mesmerizing display of atmospheric dynamics that scientists continue to study with great interest. By studying the interaction between these storms and the hexagonal formation, researchers gain valuable insights into the complex processes that govern planetary atmospheres. Saturn's unique weather patterns illustrate the stark differences between gas giants and terrestrial planets like Earth, offering a window into the forces that shape these distant worlds. The study of Saturn's atmosphere, including its hexagonal storm, not only informs our understanding of this gas giant, but also enhances our comprehension of atmospheric systems throughout the universe. Beyond its weather systems, Saturn's immense size and striking appearance further amplify its status as a celestial marvel. As the second largest planet in our solar system, Saturn's sheer size is nearly overwhelming. Its vast expanse could easily contain more than 1,000 Earths. This scale serves as a constant reminder of the grandeur of the universe, evoking a sense of awe and humility in anyone who gazes upon it. The planet's golden-hued atmosphere, with its subtle bands of color, creates an ethereal effect that is as beautiful as it is mysterious. The interplay of gases and chemical reactions within Saturn's atmosphere captures light in a way that transforms the planet into a living work of art. Yet, even as we marvel at its beauty, Saturn's rings remind us of the starkness that exists alongside its splendor. Composed of ice and rock particles, these rings form a halo around the planet, both elegant and imposing. They evoke feelings of both wonder and foreboding, a duality that mirrors the planet itself. For all its grace, Saturn is a reminder of the immense forces that have shaped it over billions of years. A reminder that the universe is a place where beauty and danger coexist in constant tension. Saturn's magnetic field is another force that shapes the environment of its moons and the surrounding space. Picture Saturn as a gigantic bar magnet, with its magnetic field extending far into the cosmos. This magnetic field is generated by the movement of metallic hydrogen within the planet's interior, creating a powerful protective shield around the planet. The most notable interaction between Saturn's magnetic field and its moons occurs with Titan, Saturn's largest moon. Titan has its own atmosphere, and Saturn's magnetic field plays a crucial role in shaping this environment. As energetic particles from the solar wind approach Titan, Saturn's magnetic field creates a protective bubble, preventing these particles from reaching the moon's surface. However, this shield comes with consequences. The interaction between Saturn's magnetic field and Titan's atmosphere causes the upper layers of the atmosphere to become ionized, releasing charged particles. These particles are then trapped within Titan's own magnetic field, creating a dynamic cycle of energy that influences the moon's atmospheric chemistry. The interplay between Saturn's magnetic field, its moons, and the surrounding space is a testament to the complex and ever-changing dynamics that govern planetary systems. As we study these forces, we gain a deeper understanding of the cosmic mechanisms that shape not just Saturn, but the entire universe. The planet's magnetic field is not just a protective force, it is a dynamic and powerful presence that plays a key role in the evolution of Saturn's moons and the wider space environment. Saturn's magnetic field is an awe-inspiring force, stretching far beyond its iconic rings and moons, influencing the surrounding space environment and the celestial bodies in its vicinity. This vast magnetic domain interacts with the charged particles that flow through the region, creating a complex and dynamic environment. It's as though Saturn's magnetic field is a master conductor, orchestrating the movement of energy, particles, and radiation in its cosmic symphony. One of the most striking consequences of this interaction is the creation of radiation belts composed of high-energy particles, a feature eerily similar to Earth's Van Allen belts. These radiation belts are not just passive structures, they actively shape the space around Saturn, impacting the moons orbiting the planet. For those moons that fall within the range of these belts, radiation exposure becomes a significant factor. The level of radiation varies depending on their proximity to Saturn, with those closer to the planet experiencing more intense radiation. This exposure doesn't simply affect the moon's surface chemistry, it could also influence the potential for life on these moons. The harsh radiation could either hinder or even shape the processes that might allow life to exist, making the study of these moons critical for understanding their habitability. The magnetic field's influence doesn't end with radiation belts, however. It plays a key role in the fascinating dynamics of Saturn's rings. The charged particles within the rings can interact with Saturn's magnetic domain, giving rise to stunning phenomena such as auroras. These colorful light displays, which occur at Saturn's poles, are caused by energized particles flowing into the planet's magnetic field, creating an ethereal glow that mirrors similar phenomena on Earth. In many ways, the auroras on Saturn serve as a reminder of the interconnectedness between the planet, its rings, and the numerous moons that orbit it. The magnetic field doesn't just passively exist in space, it actively shapes the behavior and characteristics of the moons, creating a complex dance of particles and energy. Saturn, in a sense, becomes a cosmic puppeteer, controlling the interactions that occur within its vast surroundings, affecting everything from the chemical makeup of its moons to the behavior of the particles that swirl around it. This magnetic influence underscores Saturn's position as a dominant force within the solar system, a planetary body that governs the space surrounding it with a far-reaching and persistent presence. Meanwhile, in the distant reaches of the universe, another planet captures the attention of astronomers. GJ 504b, an exoplanet located far beyond our solar system, offers a tantalizing glimpse into the early stages of planetary formation. At just 500 million years old, GJ 504b is a young world, a fledgling planet still in the formative stages of its development. This age sets it apart from many other planets, whose processes of formation and evolution have been ongoing for billions of years. The planet's youth offers a rare opportunity to study planetary development from a fresh perspective. It is a world still undergoing changes, and its characteristics have not yet fully matured. Astronomers are particularly intrigued by the planet's extraordinarily hot surface. The heat radiating from GJ 504b suggests that it still retains residual thermal energy from its formation, a relic of the intense forces that once shaped it. This heat is not just a casual detail. It opens up a range of questions about the planet's atmospheric composition, weather patterns, and the potential for unique phenomena. With such extreme temperatures, GJ 504b challenges our understanding of how planets evolve, particularly in their younger stages. The extreme warmth of GJ 504b raises the possibility that the planet's atmosphere could give rise to weather systems unlike anything we've seen on Earth. The interaction between the intense heat and the planet's atmospheric conditions could result in novel chemical compositions or weather patterns that defy conventional expectations. As scientists study GJ 504b, they are forced to reconsider what we know about planetary evolution and the processes that shape a world over time. This exoplanet acts as a case study in planetary science, a living example of the dynamic forces at play during the early stages of planetary development. Its surface temperature, combined with its young age, makes GJ 504b a captivating subject of study for astronomers looking to understand how planets form and evolve. Yet, its extreme characteristics also force scientists to confront the limitations of current theories about planetary atmospheres and the processes that shape planetary bodies. Visually, GJ 504b is a striking presence in the cosmos. The planet radiates a fiery pink hue that contrasts dramatically with the cold darkness of space. This vivid color is a direct result of the planet's extreme heat, with its surface glowing brightly in a manner that is both captivating and unsettling. The planet's intense warmth is evident in its visual appearance, as the fiery pink stands out starkly against the backdrop of the cosmos. The planet's atmosphere is likely thick with clouds composed of various chemicals, further enhancing the visual spectacle. These clouds filter the incoming light, giving GJ 504b its distinctive coloration, a striking contrast to the cold celestial bodies that surround it. The vibrant hue of the planet, while beautiful, also carries an unsettling aura. It's a reminder that while the universe may be filled with spectacular sights, it is also home to worlds that are, at times, inhospitable and mysterious. The very nature of GJ 504b's appearance invites both awe and caution. Its glowing surface suggests an environment that is both alluring and potentially dangerous, a stark reminder of the vastness and unpredictability of space. This planet is far from its star, making its internal heat and bright surface even more intriguing. The distance between GJ 504b and its star adds an element of mystery to the planet's existence. In the vastness of space, this planet's glow serves as an enigmatic beacon, a reminder of the isolation that characterizes so many of the worlds that exist beyond our solar system. The striking contrast between its warmth and its location in the cold depths of space evokes a sense of both wonder and fear, illustrating how even the most visually stunning celestial bodies can harbor an undercurrent of danger. In addition to its visual allure, GJ 504b stands out due to its position in the larger context of planetary formation. Located in the constellation of Virgo, this exoplanet is a gas giant, much like Jupiter, but it orbits a star considerably younger than our Sun. This youthfulness presents a unique opportunity for astronomers to observe the forces that shape planets in their formative stages. The planet's formation was influenced by the dust and gas present in the protoplanetary disk, And as GJ504b continues to evolve, it offers insight into the ongoing processes of planetary growth. The planet's atmosphere is constantly in flux, shaped by a combination of internal heat and external gravitational forces. This state of constant change reflects the chaotic nature of planetary formation, where collisions, mergers, and the accretion of material lead to the creation of new and unpredictable physical environments. The extreme temperature of GJ504b further underscores the early-stage nature of its development. The heat generated during its formation has not yet dissipated, and this residual thermal energy contributes to the planet's gaseous composition. The intense heat allows lighter elements such as hydrogen to remain in gaseous form, contributing to the planet's atmosphere. As planetary atmospheres evolve, they undergo constant changes. Clouds may form and dissipate, and the composition of the atmosphere shifts as different elements and compounds interact. The relationship between temperature and atmospheric chemistry plays a crucial role in determining whether certain elements will condense into clouds or remain as gases. For GJ504b, this dynamic interplay between heat and atmospheric composition makes it a fascinating subject of study, offering insights into the processes that shape planets across the cosmos. Furthermore, the conditions surrounding GJ504b suggest a continuous and complex interaction with the material in its protoplanetary disk, providing a dynamic stage for studying the gravitational forces at work. These interactions are not just a passive display. They are active agents, transferring angular momentum and influencing the planet's orbit, which could have profound implications on its evolutionary path. Such gravitational influences play a crucial role in shaping the development of a planet, determining not only its orbital mechanics, but potentially its long-term stability and physical characteristics. For instance, if GJ504b were to encounter larger bodies within the disk, perhaps rogue planetesimals or aggregations of dust and gas, it could absorb substantial mass. This mass accretion would likely alter its size and atmospheric composition, leading to profound changes in its environmental characteristics. Simultaneously, this mass absorption could disturb the surrounding disk, altering its structure and the interactions between different elements of the disk itself. Such forces can have cascading effects, making GJ504b a dynamic and ever-evolving body within the cosmic arena. GJ504b thus stands as a living laboratory for planetary formation, an active participant in the very processes that shape the universe's celestial bodies. Its existence reflects the conditions of planet formation while also being actively sculpted by them. The complexities embedded in its atmospheric dynamics, temperature fluctuations, and ongoing interactions with surrounding material underscore how delicate and tumultuous the formation of a planet truly is. These factors remind us that even in the vast, distant reaches of the cosmos, the act of creating worlds is far from static. Rather, it is a turbulent, ongoing saga of cosmic birth, growth, and transformation. This exoplanet, orbiting the star GJ504, offers an extraordinary anomaly that challenges our conventional understanding of planetary systems. Unlike the gas giants found in our own solar system, GJ504b is strikingly large, with a hue that suggests a remarkable deviation from the norms we expect from planets of its type. Its surface exhibits a vibrant pinkish glow, an unusual color that hints at a unique atmospheric composition and temperature structure, far removed from the gas giants that we are more familiar with. This color itself implies a different kind of environmental conditions than most known planetary systems, calling into question the very assumptions we've made about planetary climates and formations. Typically, planets form within a swirling disk of gas and dust around their parent stars, where the distance from the star influences the planet's final characteristics. Planets closer to the star tend to become rocky, while those situated farther out tend to accumulate more gas, eventually evolving into gas giants. However, GJ504b presents an intriguing exception to this well-established model. Located farther from its star than Neptune is from our Sun, it challenges our expectations about what a planet at such a distance should look like. Its mass suggests that it should have formed in a manner similar to that of a gas giant during the early stages of the universe's formation. Yet, the exact mechanisms behind its formation remain the subject of intense and ongoing research. as this planet defies easy classification. Adding to the mystery is the unusually low temperature of GJ504b, which sets it apart from other planets of similar size in our own solar system. While most gas giants such as Jupiter or Saturn possess significantly higher temperatures due to their size and proximity to their stars, GJ504b's temperature is more akin to that of some brown dwarfs, objects that lie between the classifications of planets and stars. This blurs the line between what we consider a planet and what might be considered a failed star, raising profound questions about the processes that lead to the formation of such bodies. Did GJ504b form through the collapse and condensation of gas, much like a star? Or did it emerge through a more unconventional aggregation of material, a process distinct from what we typically associate with stellar or planetary formation? This extraordinary discovery forces astronomers to rethink the diversity and complexity of planetary systems in ways we never imagined. GJ504b exemplifies the potential for unexpected outcomes in the cosmos, suggesting that the variety of planetary types we may encounter is far greater than the models we have traditionally used to understand the universe. As we continue to explore the farthest reaches of space, this planet serves as a reminder that our knowledge of the cosmos is still evolving, and that the universe holds far more surprises than we could have anticipated. The discovery of GJ504b is just one example of how planetary diversity is likely more expansive than our current models suggest. Imagine the implications if more planets like GJ504b were discovered. Such findings could fundamentally alter our understanding of what a planet is, what it can become, and how it evolves. It would challenge our perceptions of planetary classification and, in doing so, invite a new era of cosmic exploration where the boundaries between what constitutes a planet, a star, or something in between become increasingly blurred. The universe, it seems, is far more complex and diverse than we had ever imagined, and we have only begun to scratch the surface of its many mysteries.